Welcome back to Boring History for Sleep, the place where the world slows down, the lights grow dim, and the mind finally lets go. Tonight, we drift somewhere very few human beings have ever gone, not because no one has tried, but because the planet itself seems unwilling to let us in. We are traveling to the roof of the Earth, past the last research stations, past the final radio signals, down into a hidden realm that has been sealed shut since long before there were people to wonder about it. Before we begin, get comfortable. Dim the lights if you haven't already. Pull the blanket up just a little higher. Tonight's story unfolds slowly, the way ice itself moves, patient, quiet, and almost imperceptible. There is nothing urgent about what we're going to explore tonight. In fact, that's rather the point. Some of the oldest and stillest places on Earth are waiting for us beneath the polar ice, and we're going to ease our way toward them, one gentle layer at a time. If stories like this help you unwind at the end of a long day, you're welcome to rest here as long as you like. Let your eyes close whenever they're ready. You won't miss anything important. The ice we're about to describe has been waiting for millions of years. It can wait a little longer for you to drift off. Now, let's begin at the top of the world. A frontier with no summit. When people picture the North Pole, they usually imagine a single, simple point. A flag stuck into an endless field of white, a place you could walk to and stand upon, cold but conquerable. That image, comforting as it is, has almost nothing to do with the reality. The truth is that the geographic North Pole isn't land at all. It sits in the middle of the Arctic Ocean, a body of frigid seawater capped by a drifting, cracking, ever-shifting layer of sea ice. Unlike the South Pole, where an entire continent lies buried beneath the ice, the Arctic has no solid ground underneath it at its center, only deep, dark ocean, and on top of that ocean, a skin of frozen water that never quite holds still. Ringing that frozen ocean, though, are enormous ice sheets and glaciers, spilling down from Greenland, from the islands of northern Canada, from the Arctic edges of Russia and Scandinavia. These are not modest patches of snow. Some stretch for hundreds of kilometers. Some plunge more than 3 kilometers straight down, layer upon layer of compressed winters, a slow-motion monument built from nothing but snowflakes and time. And beneath all of that ice, beneath the glaciers, beneath the frozen sea, lies a landscape that has remained almost entirely unknown to us. Rivers that have never touched open air. Lakes that have not seen a single ray of sunlight in longer than humanity has existed. Perhaps ecosystems that evolved in total isolation, cut off from everything above by a ceiling of ice so thick and so heavy that light itself cannot follow it downward. It isn't that scientists haven't tried to look. It's that, again and again, the Arctic simply refuses to be looked at. Equipment fails. Sensors freeze solid or crack under pressure. Holes drilled with painstaking care seal themselves shut again within days, as though the ice were healing a wound. The deeper anyone tries to go, the more forcefully the environment seems to push back. And that, more than anything, is what makes this particular mystery so quietly magnetic. Somewhere beneath all of that frozen weight lies a place that belongs partly to our world and partly, it seems, to some other one entirely. What a glacier actually is to understand why this hidden world resists us so completely. It helps to first understand what a glacier truly is, because it is not simply a lot of ice sitting still. A glacier is closer to a very slow river. It begins with something almost too small to matter. Individual snowflakes drifting down onto already frozen ground, one winter after another, for centuries, for millennia. Most of that snow never fully melts away. Instead, it settles, and the weight of each new snowfall presses down on everything beneath it. Over time, the loose, airy structure of snow collapses under that weight, turning first into a grainy, half-formed material called firn, and eventually, after enough centuries, into dense, solid glacial ice. Some of the glaciers ringing the Arctic are staggeringly old. Certain deep layers are estimated to be well over 1 million years old, formed from snow that fell long before modern humans walked the Earth. And these ice masses are not just thick. The combined ice sheets bordering the Arctic Ocean can reach depths of more than 3 kilometers in places, roughly the height of 3 Eiffel Towers stacked one on top of the other, and still not reaching the bottom. This is not a frozen pond. It is closer to a frozen continent, one that presses downward with a force almost impossible to picture. And when something presses down with that much weight, for that much time, strange things begin to happen beneath it. The secret life under the ice picture for a moment, the sheer scale of pressure involved. Under enough ice, the crushing weight above generates heat, not from the sun, not from the outside air, but simply from the friction and compression of the ice itself grinding against the rock below. Even though the surface temperature might sit far below freezing, the base of a thick enough glacier can actually be warm enough under that pressure to melt. That meltwater doesn't just evaporate or disappear. It pools. It carves channels through sediment. It gathers into basins and forms lakes utterly unlike anything on the surface. These are not places where sunlight sparkles on the water, where boats drift, where fish swim near the surface. These are lakes sealed in absolute blackness, cut off from oxygen, buried beneath kilometers of solid ice, and in some cases left undisturbed for hundreds of thousands of years. We know environments like this exist because scientists have already found one, not beneath the Arctic, but beneath Antarctica. Lake Vostok, a vast body of water sealed beneath nearly 4 kilometers of ice, had gone untouched, as far as we can tell, for something like 15 million years before researchers finally reached its edges. It stands to reason that the Arctic hides similar secrets of its own. Satellites can detect faint bulges and dips in the ice that hint at hidden water below. Radar can trace shadows of what might be buried lakes and rivers, but hinting is not the same as knowing. To truly understand what's down there, someone would have to go and see for themselves, and that is where the real trouble begins. While we can't simply drill down, it would seem, on the surface, like a simple engineering problem. If oil companies can drill kilometers into solid rock, why can't scientists drill a few kilometers into ice? The answer is that ice does not behave like rock at all. Ice is layered, riddled with air pockets cracked in places. And this is the crucial part, constantly moving. The deeper you drill, the more the ice around the hole begins to behave less like a solid and more like an extremely slow-moving liquid, oozing back in to fill whatever gap you've just created. Traditional drilling rigs are built to operate on stable ground. They are not designed for a medium that flows, however gradually, around anything inserted into it. Even specialized thermal drills, machines that melt their way downward instead of cutting, run into serious trouble. As they descend, the meltwater behind them can refreeze, sealing the shaft shut like a door closing on its own. The deeper the drill goes, the harder it becomes to keep that narrow tunnel open at all. And even supposing a team manages to reach the very bottom, another problem waits there for them: contamination. If the ecosystems trapped beneath the ice have truly been isolated for hundreds of thousands or millions of years, then even a single trace of modern surface bacteria carried down on a drill bit could be catastrophic, capable of overwhelming and destroying whatever fragile, ancient life exists down there before scientists ever get the chance to properly study it. Every tool, every drop of fluid, every piece of equipment lowered into the ice must be sterilized as thoroughly as anything sent into space. That kind of caution is slow. It's expensive. And under Arctic conditions, howling winds, months of total darkness, temperatures plunging far below anything comfortable, it becomes almost unbearably difficult. There's also the matter of the ice itself simply refusing to stay in one place. Unlike Antarctica, where the great ice sheets rest on solid continental rock, much of the Arctic's ice sits atop the ocean itself, or spills from land into drifting sea ice. That ice is not anchored to anything. It drifts with the currents. It cracks without warning. A drilling platform perfectly positioned one week might find itself pulled kilometers off course by the next. Sudden pressure ridges, towering walls of buckled, crushed ice, can form in hours, tearing apart anything anchored nearby. And the logistics of simply existing up there are brutal enough on their own. Temperatures can fall below -40 degrees Celsius. Winds can exceed 100 kilometers per hour. For months at a stretch, The polar night swallows the sky entirely, cutting off solar power and plunging the whole region into darkness so complete it becomes disorienting even to trained researchers. Why not just send a submarine? It's a fair question. Nuclear submarines have, after all, crossed beneath the Arctic ice cap many times over the decades, gliding silently through the frozen dark. So why not simply send one down to explore what lies beneath the glaciers themselves? The honest answer is that submarines are built for open water, not for navigating the chaotic, ever-changing maze that exists directly beneath a glacier. Where ice meets rock, or ice meets the seafloor, the terrain is anything but smooth. Caverns form and then collapse without warning. Channels twist unpredictably in 3 dimensions. In places, ice extends downward in jagged ridges called keels, some plunging hundreds of meters beneath the surface like the roots of some enormous frozen tree. Even the most advanced submarine in the world cannot safely navigate terrain it has no map for. And here lies the cruelest irony of the whole endeavor. We cannot map the world beneath the ice because we cannot get down there to see it, and we cannot get down there because we have no map to guide us. It's a closed loop, a puzzle that seems to fold back on itself no matter which direction you approach it from. Robotic probes seem, at first glance, like a promising way around the problem. Autonomous underwater vehicles, machines capable of slipping through narrow underwater passages without a human pilot, are being developed specifically for environments like this. They can go where no person safely can, but even these machines run into walls of their own. Radio signals barely penetrate solid ice at all. Sound waves, used for a kind of underwater communication, degrade quickly over long distances through such dense material. Once a robot vanishes beneath the ice, it is, for all practical purposes, entirely on its own. If it becomes stuck, or damaged, or simply lost in the dark, there is very little anyone on the surface can do about it. Battery life presents another quiet but serious obstacle. Freezing temperatures drain power far faster than machines were ever designed to handle, and there is, of course, no way to recharge a battery kilometers beneath a glacier. Most of these robotic explorers can only function for a matter of days or weeks before they need to resurface, and resurfacing simply isn't an option when you're sealed beneath solid ice, and looming over everything else is pressure. At depths of several kilometers, the sheer weight bearing down reaches hundreds of times normal atmospheric pressure. Enough, if a machine isn't engineered with extraordinary precision, to crush it as easily as a hand might crush an empty can. Let's settle back in. If you drifted off during the last section, don't worry, nothing here needs to be followed closely. Just let the words wash over you as we sink a little deeper into this quiet, frozen mystery. A kingdom made of ice. Far above the forests and rivers most of us call home, past the last roads, past even the empty tundra that stretches toward the horizon, there is a region that seems to hold its breath. Water forgets how to flow there. Air forgets how to warm. Even light seems to lose its nerve before it gets very far. This is a kingdom ruled by nothing but ice itself, ancient, shifting, and far older than any human institution. To understand why the world beneath these glaciers still eludes us, we have to first understand the kingdom above it, because it isn't simply a location. It behaves more like a force, one that presses down and conceals everything beneath it, refusing to give up its secrets easily. The Arctic ice is not, as it might appear from a satellite photo, one single unmoving sheet. In winter, the sea ice spreads out to cover something like 14 million square kilometers, an area larger than the whole of Europe. By late summer, it shrinks back to perhaps 4 or 5 million square kilometers. But even at its thinnest, this ice remains substantial, several meters deep in most places, layered with snow and old, refrozen melt that insulates the ocean below like a thick quilt. Ice that survives more than one melting season is known to scientists as multi-year ice, and it becomes progressively harder, thicker, and more stubborn with each passing winter. This is one of the single greatest obstacles standing between us and whatever lies beneath it. Below that frozen surface, the terrain only grows stranger. The Arctic ocean floor is not a smooth, uniform bowl. It's a rugged landscape of ridges, basins, and submerged plateaus. At its deepest point in the Fram Basin, the ocean plunges more than 5,000 meters down. A vast underwater mountain range known as the Lomonosov Ridge cuts across the pole like a spine, dividing the ocean into two great basins. Where ice and seafloor meet, the terrain buckles into towering pressure ridges, pools into hidden meltwater basins, and churns in slow, powerful underwater currents. No 2 meters of this hidden world are quite alike. The weight that presses everything down. Ice held in your palm feels almost delicate, something that melts at the first touch of warmth, something you could break with a light tap. But scale it up to the size of a glacier, and that fragility disappears entirely. Every square meter of glacial ice weighs somewhere around 900 kilograms for every meter of thickness. Multiply that across ice sheets that stretch for hundreds or even thousands of meters downward, and the resulting pressure becomes almost impossible to picture. The Greenland ice sheet alone, the largest single body of ice in the entire northern hemisphere, contains enough frozen water that, if it melted completely, global sea levels would rise by more than 7 meters. That's trillions of tons of ice, bearing down on the bedrock beneath it, carving valleys, grinding mountains slowly into fine silt, and sealing away whatever lies beneath under a weight beyond ordinary human comprehension. That pressure doesn't just sit there quietly either. It changes the basic physics of the ice and rock around it. It can melt ice at the base of a glacier even while the surface stays locked in a deep freeze. It reshapes the very bedrock beneath it. It creates hidden pockets where liquid water can persist in total darkness, sealed away from the surface world for thousands, sometimes millions of years. And within some of these sealed-off pockets may lie the Arctic's greatest secrets, vast, hidden networks of subglacial rivers and lakes, quietly lubricating the base of the ice sheet, gently reshaping the pace at which glaciers creep toward the sea. Some of these hidden waters may even shelter microbial life, organisms that have evolved in near-total isolation, drawing energy not from sunlight but from minerals in the surrounding bedrock. If such life exists, it might offer us a preview of what could be waiting beneath the icy crusts of moons like Europa or Enceladus, worlds where oceans are thought to hide beneath kilometers of frozen shell. To even get a glimpse of these hidden environments, scientists lean on an assortment of remote sensing tools. Satellites capable of measuring the tiniest shifts in the surface of the ice can hint at liquid water pooling far below. Radar systems flown over the ice can trace out its internal layering, occasionally revealing what might be a buried lake. Seismic surveys, essentially listening for the echo of sound waves traveling through ice and rock, offer further clues. But all of these tools share the same fundamental limitation. They can tell us that something is down there. They cannot show us what it actually is. A lesson from the bottom of the world. Long before anyone attempted anything like this in the Arctic, researchers tried it in Antarctica, at a place called Lake Vostok, a body of water sealed beneath nearly 4 kilometers of solid ice. Russian scientists spent decades slowly, carefully drilling downward, using a careful combination of mechanical drilling and heat, working to avoid contaminating whatever lay below. Even with all of that caution, the project faced repeated setbacks. Drill shafts froze solid and had to be reopened. Equipment failed under the brutal cold. Concerns about contaminating the ancient lake delayed the project for years at a stretch. It wasn't until 2012 that the team finally broke through to the water below, and even then, the results were more puzzling than triumphant. The samples they retrieved were difficult to interpret, and much about what actually exists inside that lake remains uncertain to this day. If reaching a lake sealed beneath stable, land-bound ice was that difficult, one can only imagine how much harder the task becomes in the Arctic, where the ice is generally thinner, but also far less stable, floating rather than anchored to solid ground, constantly shifting with the currents beneath it. A region divided by borders and seasons. There's also a quieter, more human obstacle standing in the way of Arctic exploration: geography and politics. 8 different nations border the Arctic: Canada, Denmark by way of Greenland, Finland, Iceland, Norway, Russia, Sweden, and the United States, each with its own territorial claims, environmental rules, and strategic interests. Coordinating serious scientific research across that patchwork of competing interests is often nearly as difficult as the science itself. Funding for large polar expeditions is limited and fiercely competitive. Field seasons are brutally short, often confined to just a few months when the weather is even marginally survivable. Every expedition requires an enormous support structure: ice-breaking ships to cut paths through the frozen ocean, aircraft to ferry in supplies, and teams of engineers and scientists willing to spend months living and working in one of the most hostile environments our planet has to offer. Every kilogram of equipment has to be flown or shipped enormous distances. Every liter of fuel has to be carefully rationed. And every mistake in a place this remote carries the potential to be genuinely fatal. Storms can appear with almost no warning, carrying winds strong enough to tear equipment loose and scatter it across the ice. The sea ice itself can crack open beneath someone's feet without notice, forming sudden gaps known as leads that can swallow machinery or people whole. In winter, months of unbroken darkness turn simple navigation into guesswork and render solar power completely useless. In summer, when the sun barely sets at all, the surface ice softens into slush that bogs down vehicles and slows every task to a crawl. And yet, for all its hostility, the Arctic is quietly one of the most important regions on the entire planet. Its ice reflects sunlight back into space, helping regulate the planet's overall temperature. Its cold waters help drive the ocean currents that shape weather patterns across the globe. Its glaciers hold enormous archives of climate history, each layer of snow and ice recording centuries of atmospheric change like the rings of some impossibly slow-growing tree. And its hidden ecosystems, sparse as they may be, form a quiet but vital link in the broader chain of life on Earth. Ice that remembers being something else. It's worth pausing here to remember that this frozen kingdom hasn't always looked the way it does now. Millions of years ago, there were long stretches of time when the Arctic was entirely ice-free, covered instead in forests. At other points, ice extended far beyond its current boundaries, spreading deep into what are now much warmer, temperate regions of the world. Even within the relatively short span of human history, the Arctic has changed dramatically. During the last ice age, global sea levels sat more than 120 meters lower than they do today, and enormous glaciers stretched across huge portions of the northern hemisphere. As the climate slowly warmed afterward, those glaciers retreated, leaving behind the landscapes we recognize today. Now the Arctic is changing again, faster than at almost any other point in the geological record. Sea ice is thinning. Glaciers are retreating. The delicate balance that has held steady for thousands of years is quietly shifting beneath our feet, even as our tools for studying it slowly, gradually improve. It's easy, standing on the surface, to forget just how much complexity lies hidden below. The Arctic looks empty, silent, a blank, frozen page. But underneath that stillness lies a hidden world every bit as intricate as a rainforest or a coral reef, subglacial channels that may carry meltwater for hundreds of kilometers, sediments that quietly record the rise and fall of ancient ice ages, and just possibly, forms of life that have never once felt the warmth of the sun. These are the treasures held inside this frozen kingdom. For now, at least, they remain just beyond our reach, sealed away by forces we have not yet learned how to fully overcome. Settle in again. This next part moves slowly, the way the ice itself moves, patient, heavy, and almost too gradual to notice. There's no need to hold on to every detail. Just let it drift past you like snow falling outside a window, something that looks fragile but isn't if you were standing somewhere near the top of the world and pressed your bare hand against the surface of the ice. You might assume you were touching something delicate. Ice, after all, cracks under a hammer. It melts in warm hands. A child can shatter a thin sheet of it on a frozen puddle without much effort at all. But that fragile impression only holds true for ice in small quantities. Scale it up to the size of a glacier, layer it, compress it, stack century upon century of snowfall on top of itself, and it becomes something else entirely. Something ancient, something monstrous in scale, something so heavy that it can bend the shape of the land beneath it and quietly rewrite the geography of an entire region. This immense weight is one of the central reasons the world hidden beneath the Arctic's glaciers has remained so stubbornly out of reach. From snowflake to mountain, it begins with something almost embarrassingly small, a single snowflake, drifting down through cold air, landing silently on a surface that has already been white for longer than anyone can remember. Most snow that falls in temperate regions melts away with the changing seasons. But in the deep cold of the high Arctic, much of it never gets the chance. Instead, it simply stays, and more snow falls on top of it, year after year, century after century. The snow at the very bottom of that accumulating pile begins to feel the weight of everything above it. Its loose, airy structure, full of tiny pockets of trapped air, starts to collapse under that pressure. It becomes denser, grainier, transforming first into a substance called firn, something between snow and true ice. Given enough time, often centuries, that firn compresses further still, squeezing out the last of the trapped air, until it becomes dense, solid glacial ice. What began as something light enough to be lifted by a gust of wind has become heavy enough, in sufficient quantity, to reshape entire continents. Consider the scale involved. The Greenland ice sheet, the single largest body of ice anywhere in the northern hemisphere, contains something like 2.9 million cubic kilometers of frozen water. That's an amount of ice so vast it could bury the entire continental United States beneath a layer more than 300 meters thick. Its total weight isn't measured in simple tons. It's measured in trillions of tons, an almost meaningless number to try to hold in your mind. Ice that moves without seeming to hear something that surprises a lot of people the first time they hear it. Glaciers move. Not quickly. Nothing about a glacier happens quickly, at least not by ordinary human standards, but they move nonetheless, flowing outward from their thickest points toward lower ground, and eventually toward the sea. Under the sheer, relentless pressure of its own weight, glacial ice behaves less like a rigid solid and more like an unbelievably slow, thick liquid, deforming steadily as gravity pulls it downhill. This movement isn't uniform across a glacier. It depends on temperature, on the friction between ice and the bedrock beneath it, on the presence or absence of meltwater acting as a kind of lubricant, and on a dozen other subtle factors. But no part of a glacier, however solid it looks from a distance, is ever truly standing still. Even the thickest sections creep forward by a few millimeters or centimeters each day, a pace invisible to the eye, but unstoppable over the span of years. For every machine we've ever tried to send down into this frozen world, that constant, quiet motion has proven to be a formidable adversary. It bends drilling shafts out of alignment. It slowly closes tunnels that were carefully carved open. It crushes instruments that are left in place too long, folding them into the ice like a fossil forming in slow motion. Numbers that are hard to hold in the mind to really appreciate just how overwhelming this pressure becomes. It helps to look at some rough figures. For roughly every 10 meters of ice stacked above a given point, the pressure increases by about 1 additional atmosphere, something in the neighborhood of 15 pounds per square inch. That means beneath 1,000 meters of ice, pressure already exceeds 100 atmospheres. At 3,000 meters, a depth reached at the base of parts of the Greenland ice sheet, pressure climbs past 300 atmospheres, somewhere around 4,000 pounds bearing down on every single square inch. Very few materials on Earth can endure that kind of sustained force forever without eventually deforming. Steel bends. Glass shatters under the wrong kind of stress. Even solid rock, given enough time, will slowly flow like a thick liquid. Under that same pressure, even water begins behaving strangely. Its freezing point actually drops, meaning that liquid water can exist at the base of a glacier even when the surrounding temperature sits comfortably below zero. That's precisely why thin films, and sometimes much larger pockets of meltwater can be found underneath even the coldest, thickest glaciers. This water plays a critical role, acting as a natural lubricant that helps the enormous mass of ice above slide more easily over the bedrock below. For anyone trying to explore this hidden world, that meltwater is both a fascinating clue and a serious hazard. A drill might be grinding steadily through solid ice for kilometers, only to suddenly punch through into a hidden pocket of liquid water, destabilizing the entire borehole in an instant, and raising the immediate risk of contaminating whatever pristine environment lies just beyond. A landscape being reshaped from below the pressure doesn't act only in a straight, downward line, either. As a glacier flows outward, it exerts tremendous horizontal force as well, grinding against valley walls, scraping across the bedrock beneath it. This slow, relentless process, known as glacial erosion, is responsible for carving out some of the most dramatic landscapes on the planet. Deep U-shaped valleys, fjords, entire basins that were once buried beneath ice a mile deep or more. But it also means that the interface between ice and rock is never truly stable. Hidden cavities open, then collapse. Water channels shift course. Sediment piles up in one place, only to be swept away and redeposited somewhere else entirely. For any machine attempting to operate in this kind of environment, predictability becomes almost impossible. A channel that existed when a mission was first planned may have vanished or moved entirely by the time equipment actually arrives. This same immense pressure also reshapes the land itself. On a scale that stretches far beyond the ice alone, the Earth's crust, though it feels perfectly rigid beneath our feet, is actually somewhat elastic over long timescales. When a massive ice sheet forms, its weight gradually pushes the crust downward, sometimes by hundreds of meters. When that ice eventually melts away, the crust slowly springs back upward again, a process scientists call isostatic rebound. This rebound can take many thousands of years to complete. In places like parts of Canada and Scandinavia, the ground is still measurably rising today. A slow, ongoing recovery from the weight of ice sheets that disappeared more than 10,000 years ago. Beneath the Arctic's remaining glaciers, this same interplay between ice and rock continues even now. As the ice thickens or thins, advances or retreats, it flexes the crust below, subtly altering the flow of groundwater and reshaping the very foundations of the landscape hidden underneath it. Even the ocean feels the weight. It isn't only the land that carries this burden. The ocean beneath the floating Arctic sea ice feels it too. Sea ice may be far thinner than the towering ice sheets of Greenland, but spread across millions of square kilometers, it still presses down with meaningful weight, subtly altering currents and mixing patterns in the water below. Combined with the pressure exerted by glaciers spilling into the sea from the surrounding coastlines, this weight helps shape the broader circulation of the entire Arctic Ocean, which in turn influences the distribution of nutrients, the formation of deep water masses, and even weather patterns that stretch far beyond the Arctic itself. The Arctic functions almost like a piston in the enormous, slow-moving engine of Earth's climate system. Any attempt to explore beneath its ice has to reckon not just with the ice, but with this whole intertwined system of ocean and pressure working together. Why our machines struggle so much for engineers designing equipment to operate in this world, all of this pressure amounts to a fundamental barrier. Most drilling technology was designed with rock in mind, a relatively stable, predictable material. Ice is almost the opposite. It flows. It melts and refreezes without warning. It applies force unevenly and unpredictably. Drill shafts can buckle under the sideways pressure of shifting ice. Boreholes can slowly seal themselves shut as the surrounding ice creeps back inward. Meltwater can refreeze directly above a drill, trapping it deep within the glacier with no way back to the surface. And even when equipment does survive the long journey downward, the conditions waiting at the bottom, crushing pressure, unpredictable pockets of water shifting sediment, can render it useless within moments. The same challenge applies to robotic submersibles designed to explore beneath the ice. Their outer hulls need to be strong enough to resist being crushed, yet light enough to remain maneuverable. Their sensors have to function reliably in near-total darkness and extreme cold. Their power systems must keep working even as temperatures plunge and pressure climbs relentlessly. And they must manage all of this while operating almost entirely alone, since neither radio waves nor sound signals travel well through kilometers of solid ice. A single failure, deep beneath a glacier, doesn't just mean the loss of an expensive piece of equipment. It often means the loss of years of careful planning, along with any data that machine might have collected. A kind of pressure measured in time. There's another, quieter dimension to all of this weight, one that has less to do with physics and more to do with time itself. Every layer of ice represents a single winter, a season of snowfall that fell and then simply never melted away again. In some places, the ice sitting at the very base of the Greenland ice sheet is estimated to be more than 1,000,000 years old. That means any water trapped beneath it has remained sealed away since long before anything resembling a modern human ever existed. In that sense, the pressure explorers face down there isn't only physical. It's temporal as well, the accumulated weight of countless winters, pressing down season after season, century after century, until the past itself becomes a kind of barrier. Every attempt to drill through that ice is, in a very real sense, an attempt to reach backward through time, to touch a world that has remained untouched for longer than we can properly comprehend. And yet, even that ancient weight is not fixed in place forever. As the climate warms, glaciers thin and retreat, gradually reducing the weight they exert on the land beneath them. This can trigger the slow rebound of the crust, altering drainage patterns, and in some cases exposing hidden subglacial environments to conditions they haven't experienced in millennia. It can also destabilize the ice sheets themselves, accelerating their movement and increasing the frequency of large chunks of ice breaking away into the sea. For anyone trying to study this hidden world, that means the target keeps shifting even as the tools to study it slowly improve. A site chosen for a future drilling expedition might become unstable long before the project ever begins. A channel carefully mapped one year might be completely gone by the next. The weight of 1,000,000 winters, in other words, is not a static obstacle. It is a living, shifting one, heavy, ancient, and still very much in motion. Let your shoulders drop a little. Let your breathing slow. We're heading now into the deepest, quietest part of tonight's story. A darkness so complete it barely resembles the darkness we know from closing our eyes at night. A darkness that endures far beneath the frozen skin of the Arctic, where no sunlight has ever reached and no eye has ever seen. There exists a kind of darkness that doesn't simply exist, it endures. It is older than the earliest human stories. Older than the first tools ever carved from stone. Older, in some cases, than the very shape of the continents we now recognize. It has remained unbroken for millions of years, sealed away beneath the weight of ice and the slow indifference of time. This is the darkness we would have to travel through if we ever hope to truly explore the hidden world beneath the North Pole's glaciers. It isn't the kind of darkness that comes with a sunset or the flick of a light switch. Those are thin, temporary veils, easily pierced by a candle or a flashlight. This is something closer to absolute. It is the product of kilometers of ice, each meter scattering, absorbing, and blocking nearly every trace of light attempting to pass through it. Even in the clearest ice imaginable, sunlight only manages to penetrate a few dozen meters before fading away entirely. Beyond that point, even the faintest whisper of daylight simply ceases to exist. Go deeper still, and the ice itself becomes clouded, filled with ancient trapped air bubbles, sediment, and countless layers formed by thousands of individual winters. By the time you reach the base of a truly thick glacier, perhaps 2 or 3 kilometers down, light isn't just absent. It becomes, in a sense, entirely irrelevant. There is nothing left for it to illuminate, nothing for it to reveal. The darkness there simply is, the way stone is stone or water is water. A world built without light. This total absence of light creates conditions that feel almost otherworldly. Human senses, after all, are built around light. Our eyes evolved specifically to detect it. Our internal biological clocks depend on cycles of daylight and darkness to regulate sleep and wakefulness. Even our sense of space and movement leans heavily on visual information. Take that light away entirely, and those senses simply falter. Cameras become useless without artificial illumination. Lasers scatter unpredictably when passing through cloudy, bubble-filled ice. Sonar, sound waves bounced off distant surfaces, can offer only rough, blurry outlines of whatever lies beyond. Every attempt to explore this environment starts to feel a bit like groping blindly through an endless void, with each measurement incomplete, each piece of data shadowed by uncertainty. And this darkness is more than simply a lack of light. It also represents total isolation. If ecosystems exist within this hidden world, they've been sealed away from the surface for perhaps hundreds of thousands or even millions of years. They have never experienced a sunrise, never known the changing of seasons in any way we would recognize. Whatever rhythms govern their existence, if any, are dictated entirely by different forces. The slow trickle of meltwater, chemical reactions between rock and water, faint traces of geothermal heat rising up from deep below. In a place like that, life, if it exists at all, would have to survive without photosynthesis entirely, relying instead on something called chemosynthesis, extracting usable energy directly from chemical reactions rather than sunlight. We already know environments like this exist elsewhere on Earth. Around deep-sea hydrothermal vents, far below any trace of daylight, entire communities of organisms thrive on nothing but the minerals released by volcanic activity on the seafloor. If something similar exists beneath the Arctic's ice, it would represent not just an unusual adaptation, but an entirely different way of sustaining life. One that has apparently thrived far beyond the reach of sunlight for longer than our species has been around to wonder about it. Life that might rewrite the rules. This possibility is, quite understandably, one of the most exciting reasons scientists are so determined to reach these hidden worlds. Over the past several decades, we've discovered so-called extremophiles, organisms capable of surviving in conditions once thought completely incompatible with life, thriving in boiling hot springs, deep inside nuclear reactors, buried far within the Earth's crust, and sealed beneath kilometers of Antarctic ice. If similar organisms exist beneath the Arctic's glaciers as well, it would add yet another entry to this growing list of environments where biology seems to defy our expectations. More importantly, it might offer meaningful clues about how life could exist elsewhere in the solar system entirely. Icy moons like Europa and Enceladus are believed to hide entire oceans beneath thick crusts of frozen water. If life can somehow persist in the lightless, pressurized, chemically driven world beneath our own North Pole, then perhaps it could exist in those distant, alien oceans as well. In that sense, exploring this darkness isn't only about understanding our own planet. It's about probing the very edges of what life itself might be capable of, anywhere in the universe. Even setting aside the question of life entirely, this darkness still holds secrets well worth pursuing. Sediments trapped beneath the ice may contain a detailed record of Earth's climate stretching back hundreds of thousands, possibly millions of years. Every individual layer functions almost like a page in that record, quietly preserving changes in temperature, atmospheric composition, ocean circulation, even ancient volcanic activity. Successfully reaching and reading those layers could help scientists reconstruct much of Earth's climatic history, and in turn, sharpen our understanding of where the climate might be headed next. But those sediment layers remain sealed beneath both ice and total darkness, protected by conditions that make them extraordinarily difficult to reach. Drilling through kilometers of solid ice is challenging enough on its own. Extracting clean, uncontaminated samples from a pitch-black, high-pressure, often waterlogged environment at the very bottom is harder still. And even successfully retrieving a sample doesn't guarantee easy answers. Interpreting exactly what those layers mean is its own complicated puzzle, one we're still learning how to properly read. A balance that can shift without warning. This same darkness also shapes the physical environment in subtle but important ways. Without any sunlight reaching the base of a glacier, temperatures there remain consistently low, usually well below freezing. The overlying ice acts almost like insulation, trapping faint geothermal heat rising from below and creating a delicate, easily disturbed balance between freezing and melting. Even a small shift in temperature or pressure can tip that balance dramatically. A slight increase in heat might carve open a brand new meltwater channel where none existed before. A slight decrease might just as easily seal an existing passage completely shut. These shifts can happen suddenly and unpredictably, and they can render carefully planned exploration missions obsolete almost overnight. A borehole that reaches liquid water one year might strike nothing but solid ice the next. A channel carefully mapped using radar might have vanished entirely by the time a probe finally arrives to explore it. The darkness conceals these changes from us almost completely, leaving scientists to piece together what's happening from scattered, indirect evidence and educated guesswork. The psychological weight of total darkness there is also a quieter, more human dimension to all of this, something not often discussed, but genuinely significant for anyone attempting to work in environments like this. Human beings simply aren't built for absolute darkness. Even in the deepest parts of the ocean, faint traces of bioluminescent light occasionally flicker through the black. Beneath the Arctic's glaciers, there may be no light at all, in any form. For scientists and engineers designing missions into this world, the total absence of visual reference points can be genuinely disorienting. Time begins to lose its usual meaning without any sunrise or sunset to mark its passing. Space itself becomes strangely abstract when there's nothing at all to actually see. Even our machines struggle with this same sensory vacuum. Navigation systems built around visual landmarks become effectively useless. Cameras designed to detect light must rely entirely on artificial illumination, which risks altering the very environment scientists are hoping to observe undisturbed. Even sonar, which relies on sound rather than light, struggles to produce clear, high-resolution images within the complex, ever-shifting geometry that exists beneath a glacier. It's often said that exploring beneath Arctic ice resembles exploring outer space in certain ways. Both environments are extreme, hostile, and almost entirely alien to our ordinary human senses. Both demand technology capable of operating without constant, direct human control. Both require meticulous attention to contamination and safety, and both hold out the tantalizing possibility of discoveries that could reshape our understanding of the universe itself. But there's one crucial difference worth remembering. Space, for the most part, is empty. The darkness beneath the Arctic is anything but. It is filled with water, ice, sediment, pressure, and quite possibly, life itself. It is a darkness that may be genuinely alive in ways we can barely begin to imagine, shifting, flowing, and evolving even in the total absence of light. Why light doesn't simply solve the problem, some might reasonably wonder why darkness poses such a significant obstacle at all. After all, we already possess plenty of technology capable of generating artificial light, lamps, lasers, sensors capable of illuminating even the deepest ocean trenches on Earth. But the underlying problem isn't merely a matter of lighting the way forward. It's that light itself behaves very differently in an environment like this. In water, light scatters and fades quickly, rapidly losing both intensity and clarity. In ice, that scattering becomes even more pronounced, with trapped air bubbles and embedded sediment bending or blocking light almost entirely. Artificial illumination might reveal whatever sits directly in front of a probe, but it typically cannot pierce more than a few meters into the surrounding darkness. And even when it does manage to reveal something, that light itself changes what's being observed. It introduces heat, which can subtly disturb the delicate thermal balance of the surrounding environment. It can interfere with ongoing chemical reactions or potentially disrupt biological processes, altering the very systems researchers are hoping to study in their natural, undisturbed state. This darkness, in other words, isn't simply an obstacle standing in our way. It's a defining feature of the entire hidden world beneath the Arctic ice, one that shapes everything from the physical structure of the surrounding ice, to the chemical makeup of the trapped water, to the behavior of any potential life forms, to the long-term preservation of ancient sediment layers. Because it's so absolute, it also fundamentally shapes our ability to explore it at all. We remain, in a very real sense, creatures of light trying to navigate a world that has never known it. Every tool we design, every mission we plan, has to account for that basic, unavoidable mismatch. A reminder that not everything has been mapped there, something quietly humbling in all of this. It's a gentle reminder that not everything on our planet has been cataloged, measured, and fully understood. In an era when satellites can photograph every mountain range and drones can survey every remote forest, it's tempting to assume that nothing on Earth remains truly hidden. And yet, buried beneath the Arctic ice, sealed in darkness older than human memory itself, lies a realm that has never felt the warmth of sunlight, never echoed with the sound of footsteps, never once been properly mapped or measured by anyone. It's a gentle reminder that our planet still holds a few genuine secrets, and that some of the deepest, strangest mysteries aren't hiding in some distant galaxy or exotic alien world, but right here, beneath our own feet, closer than we ever imagined. Let your eyes rest again. We're drifting now toward the strangest chapter of tonight's story, oceans that have no shore, no waves, no surface at all. Just settle into the quiet and let it unfold. Water without a surface beneath the glaciers of the far north, in a place where light has never once reached and sound moves slowly through dense, frozen silence, there may exist entire hidden bodies of water sealed away from everything we know. They are nothing like the oceans we picture when we imagine the Pacific or the Atlantic. They don't roar with waves. They don't sparkle beneath sunlight. They have no shoreline, no tides, no surface to speak of at all. Instead, they flow quietly through tunnels and basins buried beneath kilometers of solid ice, trapped, forgotten, slowly shaped by nothing but pressure and time. If they exist in complete darkness, hidden away from the rest of the planet for perhaps hundreds of thousands or even millions of years. And they may hold secrets about the deep history of our planet, about the very nature of life itself, and about the outer limits of what exploration can achieve. Scientists refer to these hidden bodies of water as subglacial lakes, though that word barely captures what they actually are. Lake tends to conjure something calm, placid, contained. But water trapped beneath a glacier is neither of those things. Under the immense pressure found down there, even small amounts of heat generated by friction, by geothermal energy rising from deep underground, or simply by the sheer weight of the ice pressing down, can melt the base of a glacier from below. That meltwater doesn't simply sit still once it forms. It flows into low-lying depressions. It carves narrow channels through sediment. It gathers into pockets and basins, sometimes forming entire connected networks stretching for hundreds of kilometers beneath the ice. Some of these hidden pockets remain sealed for tens of thousands of years without interruption. Others connect together, forming vast underground drainage systems. Some drain suddenly and dramatically, unleashing massive floods that reshape the landscape below in a matter of days. Others sit quietly, isolated and completely undisturbed, sealed beneath ice so thick that not a single molecule of their water has touched the open atmosphere since long before humans ever existed. What we already know from Antarctica, we know these hidden oceans exist, at least in one part of the world, because we've already found them beneath Antarctica. Lake Vostok, the largest known subglacial lake on the planet, sits buried beneath nearly 4 kilometers of ice and spans an area roughly the size of Lake Ontario. It has remained sealed off from the surface world for at least 15 million years, and Vostok is far from alone. More than 400 separate subglacial lakes have been identified beneath the Antarctic ice sheet, each with its own unique shape, depth, and behavior. In Greenland, researchers have identified more than 50 subglacial lakes of their own, though most are considerably smaller than their Antarctic counterparts. And beneath the floating sea ice of the Arctic Ocean itself, though direct evidence remains scarce, computer models suggest that similar pockets of meltwater could exist wherever the right combination of pressure, geothermal heat, and underlying terrain comes together. These are the hidden oceans researchers dream about reaching, not vast, open expanses like the seas we're familiar with, but intricate, labyrinthine networks of water threading through ice, flowing quietly, completely unseen and untouched by the outside world. A place where life might not need the sun. What makes these hidden oceans so genuinely fascinating isn't just that they exist, but what they might contain. They rank among the most isolated environments anywhere on Earth, sealed off entirely from sunlight, shielded from the atmosphere, protected from any surface contamination. Some may have remained essentially undisturbed and stable for extraordinarily long stretches of time. Within them, chemical reactions driven by minerals in the surrounding bedrock, or by the slow radioactive decay of certain elements deep underground, could provide a steady, if modest, source of usable energy. If microorganisms exist within these hidden waters, they might survive entirely on that energy, forming complete ecosystems that never once rely on sunlight. Rather than photosynthesis, such life would depend on chemosynthesis, extracting energy directly from chemical reactions instead. We already know this is possible, because it's exactly how ecosystems survive around deep-sea hydrothermal vents, where sunlight never penetrates at all, and volcanic heat and chemistry sustain an entire hidden community of organisms. If similar life exists beneath our own glaciers, it would offer genuine, tangible proof that biology can persist even in total darkness, complete isolation, and crushing pressure. And the implications of that possibility stretch far beyond Earth itself. On Europa, one of Jupiter's larger moons, scientists believe an enormous global ocean lies hidden beneath a crust of ice perhaps 10 to 30 kilometers thick, containing, by some estimates, more water than every ocean on Earth combined. On Enceladus, a smaller moon orbiting Saturn, plumes of water vapor and ice periodically erupt from cracks near its south pole, offering direct evidence of a hidden subsurface ocean below. Both of these distant worlds receive very little sunlight, and both are far too cold to support liquid water anywhere near their surfaces. And yet, deep beneath their icy shells, heat generated by the gravitational pull of their host planets may keep water liquid, and just possibly sustain some form of life. Studying subglacial lakes here on Earth offers scientists a rare, valuable preview of what those distant, alien oceans might actually be like. They function almost like natural laboratories, giving us a way to study how life might arise, adapt, and survive in places far removed from sunlight and ordinary surface conditions. Archives written in sediment, these hidden oceans aren't valuable only because of what might be living inside them, either. They also function as quiet archives of Earth's own deep past. Sediment resting at the bottom of these lakes may contain detailed records of ancient climate shifts, past volcanic eruptions, even the aftermath of asteroid impacts stretching back millions of years. Gases trapped within that sediment could preserve tiny snapshots of long-vanished atmospheres. Layers of deposited material might reveal shifts in ancient ocean currents, ice sheet behavior, and long-term global temperature changes. Successfully unlocking those records could genuinely transform our understanding of how Earth's climate has changed across immense stretches of geological time, and, by extension, sharpen our predictions about how it might continue changing in the future. But actually reaching those records remains extraordinarily difficult. The very isolation that makes these lakes so scientifically valuable is also precisely what makes them so fragile. A single drilling operation, handled carelessly, could contaminate the water entirely, altering its chemistry or introducing surface microbes that could overwhelm whatever native organisms might already be there. A single miscalculation could collapse an underground channel or drain an entire lake before scientists ever get the chance to study it properly. Lakes that refuse to hold still. Part of what makes exploring these hidden oceans so challenging is that they simply refuse to stay the same over time. These lakes fill and drain in response to shifting pressure, temperature, and the slow movement of the ice above them. Some may remain stable for tens of thousands of years without much change at all. Others fill and drain again on timescales of mere decades, or sometimes even just a few years. These sudden drainage events can have genuinely dramatic consequences. When a subglacial lake drains suddenly, it can release billions of liters of water within just a few days, carving new channels beneath the ice and noticeably accelerating the glacier's overall flow toward the sea. These sudden floods, sometimes called Jökulhlaups by scientists studying similar events in Iceland, can reshape entire landscapes and even have a measurable impact on global sea levels. For researchers, this constant instability means that a target chosen for future exploration might not even exist in the same form by the time an expedition actually arrives. A lake detected by radar survey one year might have completely drained away by the following year. A channel carefully mapped during one field season might have shifted its entire course by the next. These hidden oceans, in other words, are not frozen in time in any literal sense. They are dynamic, constantly evolving systems, and that makes them simultaneously more fascinating and far more difficult to properly study. Reaching for something we can only sense indirectly. Another significant obstacle is simply how inaccessible these environments remain. Drilling through kilometers of solid ice demands enormous amounts of energy, extraordinary precision, and no small amount of patience. Traditional drilling methods, which typically rely on physically cutting through material or circulating specialized fluids, run the risk of contaminating the hidden environment below or becoming trapped entirely as the surrounding ice flows and refreezes around the equipment. Thermal drills, which melt their way downward instead of cutting, come with their own set of challenges. They require enormous amounts of power and must carefully manage the meltwater they generate to prevent it from refreezing above the equipment and sealing the borehole shut. Even when a drill successfully reaches a hidden lake, retrieving a clean sample without contamination is a remarkably delicate process. The water down there sits under considerable pressure and may surge upward into the borehole on its own, carrying sediment and surface contaminants along with it. Specialized systems have to be used to capture water and sediment cleanly, while carefully maintaining pressure conditions and protecting the fragile environment below from unnecessary disturbance. Because of all these challenges, most of what we currently know about subglacial lakes comes from indirect evidence rather than direct observation. Radar and seismic surveys can reveal a lake's general outline. Satellite measurements can detect subtle changes in surface elevation that hint at filling and draining happening far below. In certain cases, water flowing out from beneath a glacier's edge carries sediment and microorganisms that offer small clues about what might exist further upstream, hidden beneath the ice. But these glimpses remain frustratingly incomplete. They tell us these hidden oceans exist. They don't yet tell us how they truly function, what exactly they contain, or how they continue to change and evolve over time. New tools for an old problem. In recent years, scientists have developed increasingly creative approaches for reaching these remote, hidden environments. One particularly promising idea involves something called a cryobot, a self-contained robotic probe designed to melt its way steadily downward through solid ice, often powered by heat generated from a small nuclear source. Unlike traditional drilling equipment, cryobots don't need to keep a borehole open behind them. They simply move slowly downward, melting the ice ahead of them while it quietly refreezes behind, sealing their path as they go. In theory, a cryobot could descend through kilometers of ice, eventually reach a subglacial lake and deploy small instruments or even smaller robots directly into the water below. Another approach involves hot water drilling, in which high-pressure jets of heated water are used to melt a clean path directly through the ice. This particular method has already been used successfully in parts of Antarctica to reach shallower subglacial lakes, and researchers are hopeful it can eventually be adapted for the deeper, more complex conditions found in parts of the Arctic. Advances in autonomous underwater vehicles also offer real promise. These small robotic machines could potentially enter subglacial lakes through narrow openings and explore their interiors directly, mapping their shape and quietly searching for any signs of life. Despite all of this progress, the underlying challenges remain immense. Communicating through kilometers of solid ice is still extraordinarily difficult, making it hard to control robotic probes in real time or reliably retrieve their data. Power remains a serious constraint, both for drilling operations and for any sustained exploration once a probe reaches its target. And contamination remains a constant, serious concern. Every single mission has to follow strict cleanliness protocols in order to avoid permanently altering the pristine environments hidden below. Because of all this, progress in this field tends to unfold slowly, often over the span of many years or even decades. Each individual mission requires extensive planning, careful testing, and constant refinement. Each new attempt builds carefully on the lessons learned from every attempt that came before it. And each small discovery, however modest, brings us just a little bit closer to finally understanding these hidden oceans we've spent so long only dreaming about. Take a slow breath. We're moving now into the story of the machines themselves. The submarines, the drills, the small robotic explorers humanity has built to reach a world that doesn't particularly want us there. Fragile ingenuity against an ancient force for all our ambition. For all the centuries we've spent turning questions into discoveries, we remain, in many ways, fragile creatures attempting to reach into places that were never designed to welcome us. And nowhere does that fragility become more obvious than in our repeated attempts to send machines into the frozen world beneath the Arctic's glaciers. Every carefully engineered drill, every meticulously designed probe, represents an impressive feat of human ingenuity. And yet, standing against ice that weighs trillions of tons, water that moves invisibly through total darkness, and pressure capable of crushing a submarine as easily as an empty can, our machines can start to look almost embarrassingly small. They are built to touch what we cannot touch ourselves, to see what our own eyes will never see. And still, for now, that hidden world remains mostly beyond even their reach. Humanity has been building machines to survive hostile environments for a very long time. Submersibles engineered to withstand the crushing pressure of the deep ocean, rovers built to crawl across the surface of distant planets, spacecraft designed to endure the empty cold of space beyond our own atmosphere. But the environment hidden beneath the Arctic's glaciers is unlike any of these. It's a place where ice behaves simultaneously like both a solid and a slow-moving liquid, where water flows under pressures hundreds of times greater than what we experience at the surface, where reliable communication is nearly impossible, and where nearly everything, temperature, structure, chemical composition, shifts constantly and unpredictably. Tools built for one extreme environment simply don't translate easily to another. Submarines beneath the ice, one of the earliest tools humanity ever used to peer beneath the Arctic ice, was the nuclear submarine. During the Cold War, both American and Soviet vessels regularly slipped beneath the polar ice cap, navigating largely blind through a shifting maze of drifting ice flows and jagged underwater ridges. These missions represented remarkable achievements in both engineering and navigation, proving conclusively that human crews could travel safely beneath thick ice for extended stretches of time. But even these enormous, powerful vessels had clear limitations. They traveled beneath floating sea ice, not beneath the far more chaotic terrain found under land-based glaciers. They generally stayed within open water, well away from the tangled, unpredictable zones where ice meets solid rock or land. And while they were certainly capable of mapping the underside of the sea ice and gathering useful data about the surrounding water, they never came close to reaching the deep, pressurized zones beneath grounded ice sheets, the places where hidden subglacial lakes and rivers are believed to exist. For all their raw power, submarines are simply too large, too blunt an instrument for the kind of careful, precise exploration this particular environment demands. Drilling down from above to reach any deeper, scientists eventually turned to a more direct approach, drilling straight down through the ice itself. The basic logic seemed simple enough. If we can't reach this hidden world from below, perhaps we can reach it from above instead. Drilling into glaciers isn't new, of course. Ice cores have been extracted for decades as a way of studying past climate conditions preserved layer by layer within the ice. But drilling all the way down to the very base of a glacier is an entirely different challenge. It's slow. It's difficult. It's remarkably expensive. The ice itself isn't uniform. Its composition, density, and temperature all shift as you descend, with compressed layers of recent snow eventually giving way to much older ice riddled with trapped air bubbles and ancient sediment. Pressure steadily increases the whole way down, and at a certain depth, the ice itself begins behaving almost plastically, slowly flowing back around the borehole and threatening to seal it shut entirely. Traditional rotary drills, which work reasonably well when cutting through solid rock, struggle badly in this environment. They typically rely on circulating fluids to carry loose material back up to the surface and to help prevent the borehole from collapsing. But those same fluids risk contaminating the pristine environment waiting below. They also require constant, careful temperature management to prevent everything from simply refreezing solid. Even under the best conditions, drilling a single borehole all the way to the base of a glacier can take years of sustained effort. A single serious mistake can mean starting the entire process over from scratch. Thermal drilling offers something of an alternative approach. Rather than cutting through the ice mechanically, these systems melt their way downward using heated water or specialized heating elements. Hot water drills, in particular, have been used successfully in parts of Antarctica, where they've managed to melt through several kilometers of ice in a matter of weeks rather than years. They also tend to leave behind clean, relatively wide boreholes, capable of accommodating scientific instruments and sampling equipment. But even these systems come with real limitations. They demand enormous amounts of energy, typically supplied by fuel that has to be transported thousands of kilometers into some of the most remote regions on the planet. They require careful, constant management of refreezing water, which can just as easily seal a borehole shut or trap valuable equipment deep within the ice. And they remain fundamentally limited by the unpredictable nature of the ice itself. A sudden shift in temperature or pressure can alter the melting rate unexpectedly, while a hidden layer of sediment or a sudden influx of meltwater can redirect the entire drilling process in ways no one anticipated. The constant fear of contamination to address the serious risk of contaminating these ancient, isolated environments, scientists have developed increasingly sophisticated sterile drilling techniques designed to minimize the chances of introducing foreign microbes into subglacial ecosystems. These systems typically rely on specially treated drilling fluids, closed-loop circulation systems that never come into direct contact with the surface environment, and painstaking decontamination protocols applied to every single piece of equipment before it goes anywhere near the ice. Even with all of these precautions in place, the risk never fully disappears. A single stray contaminant, introduced into a sealed subglacial lake, could potentially and irreversibly alter its delicate chemistry, or disrupt whatever fragile ecosystem might exist within it. For this reason, many research projects deliberately stop just short of actually breaching the very base of the ice, choosing instead to study the layers immediately above it. This caution comes at a real cost. though it fundamentally limits scientists' ability to directly sample the water and sediment that likely hold the most valuable clues of all. In many cases, researchers find themselves standing just meters away from the answers they're searching for, close enough to sense what's there, but still unable to actually reach out and touch it. Robots that explore without us while drilling efforts push steadily downward from the surface. An entirely different category of machine approaches the problem from a different angle altogether. Autonomous underwater vehicles, commonly known as AUVs. These robotic explorers are specifically designed to operate beneath ice without any direct human control, navigating complex, unpredictable environments and quietly collecting data as they travel. Some are shaped like torpedoes, built for covering long distances efficiently through open water. Others are smaller and more maneuverable, designed specifically to slip into narrow crevices and tight tunnels that larger vehicles simply couldn't fit through. Equipped with sonar systems, cameras, chemical sensors, and sometimes even small robotic arms, these machines can map the underside of the ice, measure temperature and salinity throughout the water column, and actively search for any subtle signs of biological activity. AUVs have already proven useful beneath both Antarctic ice shelves and sea ice, where they've revealed intricate networks of channels and hidden cavities carved by meltwater over time. Some have even ventured into subglacial cavities near what scientists call grounding lines, the chaotic zones where ice, water, and rock all meet in a shifting, unstable equilibrium. But even the most advanced AUVs run into serious obstacles once they venture beneath Arctic ice specifically. Navigation is one of the biggest ongoing challenges. GPS signals can't penetrate water at all, let alone thick ice, and acoustic navigation systems have limited range and resolution under these conditions. That means most AUVs are forced to rely on something called dead reckoning, calculating their position based purely on speed and heading, which naturally accumulates small errors over time. Without regular position updates, these vehicles can easily drift kilometers off their intended course without anyone realizing it until it's too late. Communication presents another serious hurdle. Radio signals simply cannot pass through thick ice at all, and acoustic signals degrade rapidly over any meaningful distance, severely limiting both bandwidth and range. Most AUVs, as a result, are forced to operate almost entirely autonomously, following pre-programmed instructions and returning to a designated rendezvous point later to have their collected data retrieved. If a vehicle becomes stuck, damaged, or simply lost somewhere along the way, there's frequently no practical way to recover it at all. Beneath a glacier, where channels twist unpredictably and shift without warning, the risk of permanently losing an expensive piece of equipment remains genuinely high. Pressure creates yet another significant challenge. At depths of several kilometers, the combined weight of overlying ice and water can exceed hundreds of atmospheres of pressure. AUVs have to be engineered specifically to withstand that kind of force without deforming or springing a leak. Their sensitive electronics and sensors must be carefully sealed and insulated against both intense cold and crushing pressure simultaneously. Even their batteries must be specially designed to function reliably in near-freezing water under extreme pressure, a combination that tends to shorten battery lifespan and reduce overall capacity. Every gram of weight and every bit of available space has to be carefully balanced between structural strength, buoyancy, and how long the vehicle can realistically operate before needing to return. And because missions beneath the ice can easily stretch on for days or weeks without any possibility of resurfacing along the way, these vehicles have to carry every bit of power they'll need from the very start. There are quite simply no charging stations waiting beneath a glacier. The cryobot, a one-way journey into the ice, perhaps the most ambitious technology currently being developed for this kind of exploration, is the cryobot, a self-contained robotic probe engineered to melt its own way steadily downward through solid ice, carrying scientific instruments along with it as it descends. Unlike conventional drilling equipment, cryobots don't require a borehole to remain open behind them at all. They move slowly, melting a path through the ice ahead of them, while the meltwater behind quietly refreezes, sealing their trail as they continue their descent. In theory, a properly designed cryobot could descend through several kilometers of solid ice, eventually reach a hidden subglacial lake, and deploy instruments or even smaller secondary robots directly into the water waiting below. It could collect samples, take detailed measurements, and transmit that data back toward the surface through a thin fiber optic cable trailing along behind it as it moves. Early prototypes of this technology have already been tested on glaciers here on Earth, and NASA has been actively exploring cryobot designs as a potential tool for future missions to icy moons like Europa. But cryobots face many of the exact same fundamental challenges as every other technology we've discussed: power, navigation, communication, and the constant, serious risk of contamination. They require enormous amounts of energy simply to melt their way downward. And once a cryobot finally reaches its intended target, retrieving it afterward may prove entirely impossible. If it becomes stuck somewhere along the way or encounters some unexpected obstacle, there's no realistic way for it to simply reverse course. These are, by design, one-way missions, bold, ambitious, and ultimately expendable. No single machine can solve this alone. Hot water drills, autonomous underwater vehicles, cryobots. Each of these technologies represents a genuinely different strategy, a different way of approaching the same fundamental problem. And yet all of them share one common limitation. They're forced to operate within an environment that, in a very real sense, doesn't want them there at all. The Arctic ice isn't a passive obstacle. It moves. It shifts. It flows and refreezes constantly, responding to changes in pressure and temperature in ways that can seal boreholes shut, crush expensive equipment, or completely reshape the surrounding terrain in the middle of an ongoing mission. The water hidden beneath the ice is equally restless. It flows through channels that can close off entirely or suddenly change course without warning. It carries sediment capable of clogging sensitive equipment or damaging delicate instruments. It can surge violently if a subglacial lake happens to drain suddenly, or it can remain perfectly still and undisturbed for centuries at a stretch. Every single machine that ventures into this environment has to contend with powerful natural forces that remain completely indifferent to its presence, forces capable of undoing years of careful planning within a matter of moments. And yet, despite all of these difficulties, genuine progress continues to be made. Every failed mission teaches engineers something new about how to design equipment better suited to these extreme conditions. Every lost probe reveals some previously unknown flaw that can eventually be corrected. Every unexpected result hints at phenomena researchers hadn't previously anticipated. The challenges here are undeniably enormous, but they aren't necessarily insurmountable. Advances in materials science continue to produce stronger, lighter equipment capable of withstanding both crushing pressure and abrasive ice. Improvements in battery technology are steadily extending how long missions can realistically last. New navigation algorithms are gradually reducing positional drift and improving overall autonomy. And innovations in communication technology, from improved acoustic modems to more resilient fiber optic tethers, are slowly expanding both the range and reliability of data transmission beneath thick ice. These incremental improvements might not sound especially dramatic on their own, but together, they represent essential steps toward a future where humanity might finally be capable of properly exploring the hidden world beneath the Arctic's glaciers. There's also a growing recognition, among researchers working in this field, that no single machine is ever likely to solve this problem entirely on its own. The environment is simply too complex, too varied, for any one tool to handle every aspect of the challenge. Instead, the future of under-ice exploration likely lies in coordinated systems, networks of complementary technologies working together toward a shared goal. A hot water drill might create the initial access point. A cryobot might then descend the rest of the way through the ice. An autonomous underwater vehicle might finally enter the hidden lake or channel beyond, exploring it directly while the other systems support it from above. Each piece of technology would play its own specific role, each one compensating for the limitations of the others. Missions built this way will inevitably be expensive, logistically demanding, and technologically ambitious. But they may ultimately represent the only realistic path toward finally overcoming the barriers that have kept this hidden Arctic world just out of reach for so long. Let yourself settle back down again. This next part is quieter still, a slow walk through the invisible rules that govern everything happening beneath the ice. There's nothing here you need to hold on to, just let it drift by. A world ruled by law, not ambition beneath the frozen ceiling of the Arctic, past the shifting sheets of drifting sea ice and the towering weight of glacial ice pressing endlessly downward. There exists a world governed by something far older and far less negotiable than human ambition. It is a world shaped entirely by pressure, temperature, density, and gravity, physical forces that behave in ways that defy almost everything about our everyday experience on the surface. Down there, water can behave almost like rock. Ice can flow like a slow, viscous liquid. Heat and cold meet in a fragile, ever-shifting balance. And even the strongest materials humanity has ever engineered can bend, buckle, and eventually break. This is a realm that has no interest in our goals, our timelines, or our carefully laid plans. It obeys only the most fundamental laws of physics, laws that have quietly shaped this hidden world for millions of years, and that will continue shaping it long after we are gone. And it is precisely these laws, more than any simple lack of technology or willpower, that stand between us and the hidden world sleeping beneath the North Pole's ice. The first law. Pressure. The most obvious of these governing forces is pressure itself. On the surface of the Earth, atmospheric pressure is something most of us never think about at all. It's simply the invisible weight of the air pressing down on us, something in the neighborhood of 15 pounds per square inch, so constant and familiar that it essentially disappears from our awareness entirely. But beneath kilometers of solid ice, pressure stops being a quiet background condition and becomes, instead, the single dominant force shaping absolutely everything. For roughly every 10 meters of ice stacked above a given point, pressure increases by about 1 additional atmosphere. At the base of Greenland's ice sheet, in places exceeding 3,000 meters thick, pressure can climb past 300 atmospheres, somewhere around 4,400 pounds bearing down on every square inch. To put that number into some kind of perspective, that's roughly equivalent to the pressure experienced 3,000 meters deep in the open ocean, a depth capable of crushing an unprotected submarine and warping even solid steel. Even highly specialized deep-sea vehicles, purpose-built to withstand the weight of kilometers of seawater, can struggle under comparable conditions. And ice, unlike water, is heavier, denser, and considerably less forgiving. This immense pressure changes the basic behavior of water itself. Under normal surface conditions, water freezes at 0 degrees Celsius. But as pressure increases, that freezing point actually drops lower. Near the base of a sufficiently thick glacier, water can remain liquid even at temperatures well below what would normally cause it to freeze solid. This means that even when the ice directly above appears completely solid and motionless, thin films, or occasionally much larger pockets, of meltwater can exist quietly between the ice and the underlying rock, moving slowly, almost imperceptibly. This meltwater acts as a natural lubricant, allowing the enormous weight of the glacier above to slide more easily across the ground below, gradually accelerating its overall flow. It also creates the hidden subglacial rivers and lakes we've already discussed, bodies of water sealed away under crushing, almost unimaginable weight. For scientists studying this hidden world, this presents a genuine dilemma. On one hand, the presence of liquid water down there is enormously exciting. It hints at hidden ecosystems, ongoing geological processes, and preserved records of past climates. On the other hand, its behavior under such extreme pressure remains genuinely unpredictable. A drill might be grinding steadily through solid ice one moment, only to suddenly break through into unexpected liquid water the next. A carefully positioned probe might enter what seems like a stable cavity, only to have that same cavity collapse without warning as pressure shifts around it. Even our most sophisticated computer models still struggle to accurately predict exactly how meltwater will move, or precisely where it might collect, beneath kilometers of shifting ice. Ice that flows like a very slow river pressure affects the ice itself in equally profound ways. Although it certainly appears solid to the eye, glacial ice is never truly static. Under sufficiently extreme pressure, it flows slowly, almost imperceptibly, but with a kind of quiet, relentless persistence. The individual molecules within the ice gradually rearrange themselves over time, allowing the entire mass to deform and creep steadily outward under its own tremendous weight. This slow flow is precisely what drives glaciers toward the sea in the first place, carving valleys and steadily reshaping the surrounding landscape as they move. But it also means the ice itself is never a fixed, unchanging barrier that can simply be drilled through once and then forgotten about. It's a living, constantly shifting mass, one perfectly capable of closing boreholes shut again, bending drilling shafts out of alignment, and slowly crushing any instrument left in place too long. A carefully excavated tunnel might last only a matter of days before it begins collapsing in on itself. A sensor placed deep within the ice might end up carried several kilometers away from its original position over the span of just a few years. For anyone attempting to conduct meaningful exploration down there, this constant, quiet movement amounts to something close to a nightmare. Nothing stays exactly where you leave it. Nothing remains perfectly stable for very long. And nothing built to operate beneath the ice can ever really assume the simple luxury of standing still. This movement isn't uniform across a glacier, either. It's shaped by countless interacting factors: temperature variations, overall ice thickness, the underlying terrain, and the presence or absence of meltwater acting as a lubricant. Warmer sections of ice tend to deform more easily than colder ones. Thicker ice generally flows faster than thinner ice sitting nearby. Ice sliding smoothly over relatively even bedrock behaves quite differently from ice grinding across rough, uneven terrain. These countless small variations create complex patterns of internal stress and strain throughout the glacier, eventually forming deep crevasses that can extend hundreds of meters down, along with distinct shear zones where different internal layers of ice slide past one another at noticeably different speeds. In some regions, a glacier's overall movement might amount to just a few centimeters each year. In others, it can suddenly surge forward by several meters within a matter of days, a phenomenon researchers refer to simply as a surge. These sudden accelerations can radically alter both the internal structure of the glacier and the hidden environment lying beneath it, sometimes within a span of just a few short weeks. A meltwater channel that existed yesterday might be completely crushed today. A previously stable cavity might collapse without any warning whatsoever. Everything scientists thought they understood about the terrain hidden beneath a particular section of ice can effectively change overnight. A restless, ever-shifting base, the very base of a glacier, where ice meets solid rock, tends to be the most dynamic and unpredictable zone of all. Pressure there is at its absolute highest. Melting is most likely to occur, and overall movement tends to be at its most chaotic. Meltwater carves winding channels directly through the underlying sediment, gradually linking hidden subglacial lakes together into loosely connected networks that fill and drain in ways that remain genuinely difficult to predict. As a glacier slides steadily across the bedrock beneath it, it plucks loose fragments of rock from the ground, carries them forward, and slowly grinds them down into fine silt. This ongoing process of erosion deepens existing valleys and widens underlying basins over time, continuously altering the overall shape of the terrain hidden below. It also creates fresh obstacles for water flow, forcing existing channels to reroute themselves and forcing hidden lakes to gradually migrate from one location to another. Sometimes the glacier itself seals a channel completely shut, trapping water within an isolated pocket that might persist for centuries afterward. Other times, a sudden drainage event releases billions of liters of water toward the sea within just a few days, carving entirely new pathways through the ice as it goes. This constant, ongoing reshaping means the entire subglacial hydrological system isn't some fixed, unchanging network at all. It's a living, evolving labyrinth, one that scientists still cannot fully map, and one that resists any attempt at reliable long-term prediction. Even the ground itself keeps moving. It isn't only the ice and water that stay in constant motion, either. The very ground beneath them shifts as well. The enormous weight of a glacier pushes steadily downward on the Earth's crust, depressing it by hundreds of meters in some particularly heavily loaded regions. When a glacier eventually thins or retreats, that crust slowly rebounds back upward again, a gradual process known as isostatic rebound, capable of subtly altering both the slope of the surrounding land and the overall direction of water flow across it. Over sufficiently long stretches of time, this slow rebound can actually shift the entire underlying drainage system. Channels that once flowed steadily northward might gradually begin flowing south instead. Lakes that once drained naturally into one particular basin might eventually spill over into a completely different one. The glacier itself responds to these gradual changes in turn, subtly adjusting its overall flow and quietly reshaping its own internal structure as a result. It's a feedback loop that unfolds across many thousands of years, one that scientists are still only beginning to properly understand. For researchers and engineers hoping to eventually explore beneath the Arctic's glaciers, this constant underlying movement represents a genuinely formidable obstacle. It means that no map of this hidden world ever stays accurate for very long. A cavity carefully identified through radar survey one year might simply be gone by the next. A borehole drilled directly toward a known water channel might miss its intended target entirely if that channel happens to shift mid-drilling. Even instruments successfully deployed can eventually be lost or damaged as the surrounding ice slowly moves around them. Fiber optic cables can snap under stress. Sensitive sensors can be gradually crushed. Carefully positioned probes can be quietly carried away from their original locations entirely. The glacier, in the end, has no particular interest in anyone's carefully laid plans. It simply moves according to its own ancient rhythms, entirely indifferent to whatever delicate strategies researchers have designed back at the surface. Two different clocks running at once. What makes all of this especially challenging is that these changes tend to unfold on wildly different timescales simultaneously. Some shifts happen gradually, over the course of many centuries, as ice slowly flows and the surrounding landscape evolves bit by bit. Others happen suddenly, surges, drainage events, sudden collapses, unfolding within a matter of hours or days. This combination of gradual, long-term change, alongside sudden, dramatic shifts, makes reliable prediction extraordinarily difficult. Computer models that work reasonably well over the span of decades often completely fail to capture events that unfold within just a few days. Instruments carefully designed for long-term monitoring can easily miss brief, but genuinely significant episodes that quietly reshape the entire surrounding environment. And because direct, continuous observation remains so limited down there, researchers frequently don't even realize a major change has occurred until well after the fact, piecing together what happened from scattered, indirect evidence gathered long after the event itself. The labyrinth beneath the ice shifts quietly in the dark, largely unwitnessed, and scientists are left to slowly reconstruct its movements from whatever fragmentary clues eventually surface. Climate as a quiet, powerful amplifier. Even the drifting sea ice covering the Arctic Ocean, thinner and far more transient than the deep glacial ice found on land, contributes its own share to this overall complexity. Driven steadily by wind and ocean currents, this ice drifts constantly across the surface of the sea, piling up into jagged pressure ridges in some places and splitting apart into open leads in others. This ongoing motion exerts real stress on glaciers wherever they happen to meet the sea, directly influencing how and where large chunks eventually break away as icebergs, a process scientists refer to as calving. Calving, in turn, can trigger sudden surges in a glacier's overall flow, or subtly alter the underlying drainage of subglacial water. It can open entirely new pathways beneath the ice, or seal existing ones shut completely. It can reshape the overall front edge of the glacier, changing how surrounding water circulates beneath it. All of these individual changes ripple steadily through the wider system, continuously altering the hidden labyrinth below in ways that remain genuinely difficult to fully anticipate. Climate change is amplifying all of this motion in ways researchers are still only beginning to properly understand. Rising temperatures are steadily thinning sea ice and accelerating overall glacial melt, increasing the total amount of meltwater, eventually reaching the base of the ice. This added water can lubricate the interface between ice and bedrock even further, speeding up overall flow and increasing how often sudden surges occur. It can also shift the underlying pressure dynamics beneath the ice, triggering unexpected drainage events and steadily altering the overall configuration of subglacial water systems throughout the region. Warmer air and ocean temperatures can undercut glaciers from below entirely, causing them to retreat more rapidly than before and further destabilizing the hidden labyrinth underneath them. These changes don't unfold uniformly, either. They vary considerably from region to region, from one individual glacier to another, and even from year to year within the same location. But collectively, they're steadily transforming this entire hidden system into something increasingly dynamic, increasingly unpredictable, and increasingly difficult to study using our current tools and methods. A puzzle that keeps rearranging itself. Our available technology continues struggling to keep pace with all of this constant motion. A single radar survey captures only a brief snapshot of a glacier's internal structure, a snapshot that may already be outdated within a matter of months. A probe carefully designed to navigate a specific set of known channels might arrive to find those channels completely gone, or dramatically altered from what was originally mapped. Drilling through constantly moving ice becomes something like trying to hit a target that keeps shifting in 3 full dimensions at once, all while the very ground beneath your own feet continues shifting as well. Even autonomous underwater vehicles, which can adapt reasonably well to certain kinds of change, remain fundamentally limited by whatever data and pre-planned routes they were given before deployment. And once a mission is genuinely underway, there's frequently no practical way to make meaningful real-time adjustments. Communication through kilometers of solid ice remains simply too slow and unreliable for that kind of responsive control. Critical decisions often have to be made in advance, based on computer models that amount, at best, to carefully educated guesses. All of this creates a peculiar kind of paradox for anyone hoping to properly study this hidden labyrinth. To truly understand how it moves and changes, researchers need reliable data. But to gather that data, they first need to place instruments directly within the labyrinth itself. And to do that effectively, they really need to already understand how the whole system moves, which, of course, they cannot fully know without the very data they're still trying to collect in the first place. It's a genuinely circular problem, one that can likely only be solved gradually, through years of incremental progress, repeated measurements, steadily improved computer models, and new missions that carefully build upon the accumulated knowledge of everything that came before them. Over time, these accumulated efforts do begin revealing certain patterns hidden within the apparent chaos, regions of relative long-term stability, recurring cycles of drainage and refreezing, meaningful relationships between surface melting and deeper subglacial flow. These emerging patterns don't eliminate uncertainty entirely, but they do gradually reduce it, offering researchers a slightly firmer foothold within an otherwise constantly shifting landscape. And yet, even as scientific understanding slowly grows, this hidden labyrinth continues quietly reminding us of its own enduring power. It isn't a puzzle that can simply be solved once and then set aside forever. It remains a living system, one that will continue evolving long after any of us are gone. Its hidden pathways will keep opening and closing. Its lakes will continue draining and slowly refilling. Its winding channels will keep twisting and rerouting themselves in ways no one can fully predict. And each time researchers return to study it, they inevitably find it somehow different from before. Breathe slowly. We're rising for a moment, away from the ice itself, to look at the invisible force reaching down from above and quietly reshaping everything below. A force that never touches the ice directly. High above the Arctic's frozen labyrinth, far removed from the hidden rivers and sealed-off lakes buried beneath the glaciers, another force is steadily at work. It moves more slowly than the tides, more quietly than the wind, and yet it carries far more influence than either. It's a force that shapes the thickness of the ice, the speed of its flow, the temperature at its base, and the behavior of the water hidden beneath it, all without ever touching that hidden world directly. That force is climate, and its influence reaches everywhere. It determines how much snow falls each winter, and how much of that snow melts away again come summer. It sets the temperature of both the air above and the ocean below. It governs how ice forms in the first place, how it flows, how it eventually fractures apart, and how it disappears entirely. And as that climate continues shifting, warming, destabilizing, it steadily reshapes the entire labyrinth beneath the glaciers, making exploration both more difficult and, in a strange way, more urgent than ever before. For most of human history, the Arctic's climate remained remarkably stable, at least by our standards. It has swung back and forth between full ice ages and warmer interglacial periods across spans of tens of thousands of years. But those changes always unfolded slowly, giving the surrounding ice plenty of time to gradually grow and retreat in long, measured cycles. Glaciers would advance, carving valleys and pushing sediment ahead of them. Then they would slowly melt back, leaving reshaped landscapes in their wake. As they withdrew, subglacial lakes would form, drain, and form again, following a rhythm shaped largely by the planet's own orbital variations and slow, gradual shifts in atmospheric composition. But over roughly the last century, that ancient rhythm has been broken. The Arctic is now warming at more than twice the pace of the rest of the planet, and that rapid, accelerating change is steadily rewriting rules that had governed this region for many thousands of years. Ice that's disappearing faster than expected. The most immediately obvious effect of this warming is the steady thinning of the ice itself. Warmer air melts ice from above, while warmer ocean water simultaneously erodes it from below. The Greenland ice sheet, which alone contains enough frozen water to raise global sea levels by more than 7 meters, is now losing mass at an accelerating rate. Satellite measurements indicate it currently sheds somewhere around 250 billion tons of ice every single year, a figure that has more than doubled within just the past few decades. Sea ice, too, is steadily vanishing. Summer sea ice coverage has declined by more than 40% since the late 1970s, and whatever ice remains tends to be noticeably thinner and younger than before, considerably more prone to melting away or breaking apart entirely. These changes aren't confined to the surface, either. They ripple downward, altering the pressure conditions at the base of the ice, shifting the temperature of the hidden water beneath it, and steadily reshaping the structure of the labyrinth below. As the ice thins, pressure at its base gradually decreases. That might sound like a small, insignificant shift, But within a system built on such delicate balances, even small changes can produce genuinely outsized effects. Lower pressure raises the melting point of water slightly, which can, in some cases, actually reduce the total amount of meltwater found at the base of a glacier. That, in turn, can increase friction between the ice and the underlying rock, slowing the glacier's flow in certain areas. But the opposite effect can just as easily occur elsewhere. Thinner ice tends to be far more sensitive to seasonal temperature variations and shifting meltwater input. Surface meltwater, which was once largely confined to shallow upper layers, can now penetrate much deeper into the glacier through crevasses and vertical shafts known as moulins, eventually carrying water all the way down to the base. Once that water reaches the bottom, it can lubricate the ice above, reducing friction and noticeably speeding up its overall movement. In some regions, this has produced a genuine paradox: glaciers that are simultaneously thinning and accelerating, surging forward toward the sea while delivering more ice into the ocean than ever before. A system being flooded from above. This surge of surface meltwater is also changing the underlying hydrology of the ice in fundamental ways. In the past, most of the water found at the base of a glacier came primarily from geothermal heat and pressure-induced melting, slow, steady processes that tended to produce relatively stable, predictable water systems over time. Now, sudden pulses of surface meltwater can flood the subglacial environment abruptly, raising water pressure rapidly, opening entirely new channels, and altering established flow paths within a very short span of time. These sudden changes can destabilize existing subglacial lakes, triggering unexpected drainage events that reshape the labyrinth below in ways no one anticipated. They can also cause noticeable fluctuations in how fast a glacier moves overall, as variations in underlying water pressure directly influence how easily the ice above can slide. For scientists hoping to eventually explore this hidden world, all of this means that conditions can shift dramatically from one season to the next, sometimes even from one week to the next. A channel carefully mapped during spring might simply no longer exist by autumn. A cavity specifically targeted for future exploration might have already drained away or shifted position entirely by the time researchers actually arrive. Warmth arriving from the sea. Warming air is only part of the story here. The oceans surrounding the Arctic ice are warming as well, and their influence runs remarkably deep. As increasingly warm water flows beneath floating ice shelves and the tongues of glaciers reaching into the sea, it steadily melts that ice from underneath, thinning it and gradually destabilizing it. This undercutting can eventually trigger large-scale calving events, where massive chunks of ice break away and drift off as icebergs, events which, in turn, can destabilize the glaciers further upstream, causing them to flow faster and thin even more rapidly than before. In Greenland specifically, many of the fastest-moving glaciers empty directly into narrow fjords, where warm Atlantic water is now intruding much farther inland than it ever has before, noticeably accelerating their overall retreat. This particular kind of ocean-driven melting is especially difficult to predict or control, largely because it depends on enormous, large-scale ocean circulation patterns that are themselves being steadily altered by broader climate change. This warming ocean water also directly affects the hidden water systems beneath the ice itself. Warmer seawater can melt more ice at the base of a glacier, increasing both the volume and overall extent of subglacial water systems. It can shift the temperature and salinity of that hidden water, altering its density and how it circulates. These shifts can influence exactly where subglacial lakes tend to form, how and when they eventually drain, and how water generally moves beneath the glacier as a whole. They can even affect the underlying chemistry of these hidden environments, altering the availability of nutrients and potential energy sources for any life that might exist down there. For exploration purposes, This adds yet another layer of genuine complexity. Instruments carefully designed around one specific set of conditions may suddenly encounter something else entirely by the time they're deployed. Computer models built using older data may simply no longer apply. The hidden labyrinth researchers are trying so hard to map isn't just constantly changing. It's changing in ways that grow increasingly difficult to anticipate with each passing year. Snow, permafrost, and a cascade of small changes. The atmosphere plays its own subtler, but equally important, role in all of this. As it warms, it holds more moisture overall, leading to noticeable shifts in regional precipitation patterns. Some parts of the Arctic are seeing increased snowfall, while others are seeing considerably less. In regions where snowfall is increasing, the added weight can actually thicken the local glacier and increase pressure at its base, potentially enhancing basal melting and further altering water flow. In regions receiving less snow, glaciers may simply thin more rapidly instead, reducing pressure and altering the underlying dynamics in a completely different direction. Even the specific timing of snowfall and seasonal melting matters a great deal. Earlier spring melts can effectively extend the overall melt season, increasing the total amount of water eventually reaching the base of the glacier. Later than usual snowfall can help insulate the ice, slowing melt and affecting underlying temperature gradients in the opposite direction. All of these individual factors interact in genuinely complex ways, continuously influencing the structure and behavior of the labyrinth hidden beneath the ice. Another consequence of this broader warming trend involves the slow thawing of permafrost, ground across much of the Arctic that has remained continuously frozen for thousands of years. As permafrost thaws, it releases water into the surrounding hydrological system, which can in turn influence glacier flow and subglacial hydrology more broadly. Thawing permafrost can also destabilize surrounding sediment, subtly altering the landscape both beneath and around nearby glaciers. In some cases, this opens entirely new pathways for water to flow through. In others, it ends up blocking channels that previously existed. Either way, it adds yet another layer of variability to an already remarkably complex system. And because permafrost thaw is itself accelerating as the broader Arctic continues to warm, its overall influence on the hidden subglacial environment is likely to keep growing in the decades ahead. A system that feeds upon itself. All of these individual changes, thinning ice, increased meltwater, warming oceans, shifting precipitation patterns, thawing permafrost, are deeply interconnected. They tend to amplify one another through feedback loops that steadily accelerate the overall transformation of the Arctic as a whole. Thinner ice becomes more vulnerable to further melting, which exposes darker underlying surfaces that absorb more heat from the sun, which then leads to even more melting. More meltwater lubricates glacier flow, increasing how much ice ultimately reaches the ocean, which contributes to global sea level rise and alters broader ocean circulation patterns, which can then bring even more warm water flowing back into the Arctic itself. These feedback loops make the entire system not just dynamic, but genuinely self-reinforcing, steadily pushing it toward conditions that grow increasingly unfamiliar and unpredictable with each passing year. For anyone hopping to explore beneath these glaciers, these accumulating changes present profound challenges. The environment down there isn't merely hostile anymore, it's becoming genuinely unstable. Conditions that once held steady for centuries can now shift meaningfully within just a few years. Baseline assumptions that once seemed perfectly reliable are increasingly becoming moving targets. Equipment carefully designed around one specific set of conditions may end up failing entirely under a different set. Long-term research plans risk becoming obsolete due to rapid changes happening on the ground. And the very features researchers are hopping to study, hidden subglacial lakes, ancient channels, potential ecosystems, may disappear or fundamentally transform before anyone ever manages to reach them. The labyrinth researchers are trying so carefully to map is, in a very real sense, being withdrawn even as they plan their next expedition. A narrow closing window. And yet, this same instability also creates unexpected opportunities. As glaciers continue thinning and retreating, they gradually expose areas that were previously completely inaccessible. As certain subglacial lakes drain away or unexpectedly connect to the surface, they occasionally offer researchers brief glimpses into environments that had otherwise remained permanently sealed off. As meltwater increases in volume, it can carry sediment, dissolved chemicals, and even microorganisms up from the base of the ice toward the surface, offering indirect evidence of what might exist hidden below. These changes, challenging as they clearly are, also open small new windows into this hidden Arctic world, reminding researchers that exploration isn't only about overcoming fixed obstacles, but also about adapting quickly to genuinely new and shifting realities. Perhaps most importantly of all, the climate's quiet, far-reaching influence forces us to confront something urgent. The world hidden beneath the Arctic ice isn't timeless in any meaningful sense. It's actively changing, and in certain cases, it may be gradually disappearing altogether. Subglacial lakes that have existed, sealed and undisturbed, for many thousands of years could potentially drain away in a single dramatic event. Ecosystems that evolved in complete isolation might be suddenly exposed and irreversibly altered. Ancient sediment layers, carefully preserving records of past climates, could be eroded away or scattered before anyone gets the chance to properly study them. If we wait too long, we risk losing the opportunity to ever study these hidden environments in their original, undisturbed state. The very same warming trend that makes exploration increasingly difficult is, at the same time, making that exploration increasingly urgent. In a very real sense, we find ourselves racing against a clock that only seems to be ticking faster with each passing year. But even amid all this complication, the climate also connects this hidden world to something considerably larger than itself. The world beneath the Arctic's glaciers isn't merely an isolated curiosity, sealed away from everything else. It's an active part of Earth's broader climate system, shaped continuously by that system, while quietly shaping it in return. The ice that thins and retreats reflects less sunlight back into space, contributing to further planetary warming. The meltwater flowing out from beneath these glaciers influences ocean circulation, weather patterns, and marine ecosystems across the entire globe. The sediments emerging from beneath the ice carry detailed records of ancient climates, offering genuine clues about where our climate might be headed next. To study what lies hidden beneath the Arctic, in other words, is really to study the climate itself, its distant past, its complicated present, and its still uncertain future. Let your mind settle again. This part of the story is gentle, almost dreamlike, a quiet wondering about whether something might be alive, right now, in a place that has never known light. A question that refuses to go away. Deep beneath the Arctic's glaciers, far removed from sunlight, wind, and every familiar rhythm of the surface world, there may exist places where life in some form has managed to endure. If such life is real, it wouldn't resemble anything found in a forest, a coral reef, or even the open ocean. It would be life shaped entirely by isolation, by total darkness, by immense pressure, and by the complete absence of nearly everything we typically assume life requires. It would be life that has never seen the sun, never breathed oxygen drawn from our atmosphere, never experienced the changing of seasons in any way we would recognize. It sounds at first almost too strange to be plausible, and yet improbable doesn't mean impossible. If anything, the broader history of life on Earth suggests quite the opposite. Wherever water, usable energy, and enough time come together, life has a curious habit of finding a way. When everything we assumed turned out to be wrong. For most of scientific history, researchers simply assumed that all life ultimately depended on sunlight. Plants convert light into usable chemical energy through photosynthesis, forming the foundation of nearly every food web on the planet. Animals eat plants, or eat other animals that eat plants. Even many of the microbes underpinning entire ecosystems rely, at least indirectly, on sunlight somewhere along the chain. Remove that light entirely, the thinking went, and life simply couldn't survive. That long-standing assumption began to unravel in 1977, when researchers exploring the Galapagos Rift on the ocean floor discovered something genuinely unexpected. Hydrothermal vents, releasing plumes of mineral-rich, superheated water directly from the Earth's crust. Clustered around these vents were thriving ecosystems unlike anything scientists had documented before: giant tube worms, clams, crabs, and countless microorganisms, all living in complete darkness, thousands of meters below any trace of sunlight. These organisms weren't relying on sunlight at all. Instead, they derived their energy through a process called chemosynthesis. Certain microbes were oxidizing hydrogen sulfide and other chemical compounds present in the vent fluid, generating usable energy and organic material in the process. Larger organisms then fed directly on those microbes, or formed close symbiotic relationships with them. An entire ecosystem, flourishing independently of the sun. That single discovery fundamentally reshaped our understanding of what life actually requires. It demonstrated, quite convincingly, that life doesn't strictly need sunlight at all. It needs usable energy, and it turns out that energy can come from a surprising number of different sources. In the decades since, researchers have discovered life thriving in places once assumed to be completely barren, deep within the Earth's crust, inside sealed Antarctic subglacial lakes, within acidic hot springs, even inside radioactive waste and permafrost tens of thousands of years old. Everywhere scientists have thought to look carefully, life seems to find some way to adapt, persist, and quietly carry on. This remarkable resilience is precisely why so many researchers now believe that if liquid water genuinely exists beneath the Arctic's glaciers, and there is every reason to believe it does, then some form of life may well exist there too. What such life might actually look like. If life does exist down there, it's almost certainly microbial. The conditions beneath the ice, total darkness, extreme pressure, near freezing temperatures, and severely limited nutrients, aren't especially conducive to large, complex organisms. But microbes, as researchers have repeatedly discovered, are remarkably versatile. They can metabolize an extraordinarily wide range of chemical compounds, survive genuinely extreme conditions, and persist for thousands of years on almost minimal amounts of energy. In certain subglacial lakes beneath Antarctica, scientists have already detected microbial life within water that had been sealed away from the atmosphere for hundreds of thousands of years. Some of these microbes appear to metabolize iron or sulfur, drawn directly from surrounding bedrock. Others rely on hydrogen, produced through ongoing chemical reactions between rock and water. Some seem to feed on dissolved organic material that has remained trapped beneath the ice since long before humans existed at all. These hidden ecosystems tend to be genuinely sparse compared to anything found on the surface, perhaps a few thousand cells in every milliliter of water, compared to millions typically found in open ocean water. But they are alive nonetheless, quietly cycling nutrients and energy within total darkness. If similar ecosystems do exist beneath the Arctic's glaciers, they could teach us an enormous amount about how life adapts to isolation and truly extreme conditions. They might reveal entirely new metabolic pathways, new ways of extracting usable energy from minerals or chemical gradients that scientists have never previously observed. They might even harbor extremely ancient lineages of microbes, ones that diverged from their surface-dwelling relatives hundreds of thousands, or perhaps millions, of years ago, offering researchers something like a living window into evolution, effectively frozen in place. And they might offer valuable clues about how life could potentially persist elsewhere in the universe entirely. The icy moons Europa and Enceladus, both believed to hide substantial oceans beneath thick shells of surface ice, present conditions strikingly similar to those found beneath Earth's own glaciers: darkness, pressure, liquid water, and chemical energy sources. If life exists there, it would likely resemble the kind of microbial ecosystems researchers suspect might exist beneath our own polar ice sheets. Studying these hidden environments here on Earth isn't just about understanding our own planet more deeply. In many ways, it's also a kind of rehearsal for the eventual search for life somewhere beyond it. Small clues hinting at something bigger. The idea of life existing beneath the Arctic's glaciers isn't purely speculative, either. There are genuinely tantalizing clues suggesting something might actually be down there. Meltwater emerging from beneath Greenland's ice sheet has been found to contain microbial communities, some of which appear to originate from deep subglacial environments rather than the surface. Sediment layers beneath various glaciers contain organic material that could potentially sustain microbial metabolism over long periods. Chemical gradients and measurable differences in the concentration of substances like iron, sulfate, and hydrogen exist within these hidden environments and could plausibly serve as usable energy sources. And we already know with reasonable confidence that liquid water does exist beneath many glaciers, sustained by a combination of pressure, friction, geothermal heat, and gradual melting. Combine water, usable energy, and enough time, and the odds of finding life improve considerably. The real question isn't necessarily whether life could exist down there. It's whether it actually does, and if so, precisely how it manages to survive. A successful first glimpse. Reaching these potential hidden ecosystems, however, remains extraordinarily difficult. All of the same fundamental barriers that make exploring subglacial lakes so challenging in general: pressure, temperature, contamination risk, and sheer inaccessibility apply here just as forcefully. Drilling through kilometers of solid ice without introducing surface microbes along the way is an extremely delicate undertaking. Even the heat generated by a drill itself can alter the local environment, melting surrounding ice, shifting chemical gradients, or potentially harming sensitive organisms nearby. Sampling water or sediment without any contamination is equally difficult. Every instrument involved has to be carefully sterilized, properly sealed, and engineered to withstand both extreme pressure and intense cold. And once samples are finally retrieved, they need to be handled with considerable care in order to properly preserve whatever microorganisms they might contain. Even with every reasonable precaution taken, distinguishing genuinely native organisms from accidental surface contaminants remains genuinely difficult. A single stray microbe introduced from the surface could potentially multiply rapidly and obscure or overwhelm the native community entirely. Despite these considerable challenges, real scientific progress has already been made. In 2013, a research team based in the United States successfully drilled into Lake Whillans, a subglacial lake buried beneath roughly 800 meters of Antarctic ice, using a specially designed hot water drill that had been carefully sterilized using both ultraviolet light and hydrogen peroxide. They successfully recovered water and sediment samples containing active, functioning microbial communities. These particular microbes appeared to be metabolizing iron, sulfur, and nitrogen compounds directly, clear evidence of a genuinely functioning ecosystem, sealed away entirely from sunlight. Similar encouraging results have since emerged from other Antarctic lakes, along with sediment samples collected from beneath parts of Greenland's ice sheet. Each new discovery strengthens the broader case that subglacial ecosystems aren't rare, isolated exceptions, but rather a fairly widespread feature of icy environments generally. If similar ecosystems genuinely exist beneath the Arctic's own glaciers, they could potentially number in the trillions, quietly forming an entire hidden biosphere sealed beneath the ice. Why this possibility matters so much. The implications of discovering such a hidden biosphere would be genuinely profound. For one thing, it would meaningfully expand our understanding of the fundamental limits of life itself. We already understood that life can survive without any sunlight at all, but subglacial ecosystems push that resilience further still. They suggest that life can potentially persist in total isolation for hundreds of thousands of years, sustained by nothing more than a slow, steady trickle of chemical energy drawn from surrounding rock and water. They suggest that life, rather than being fragile and rare, might actually be remarkably robust and adaptable, capable of thriving even under conditions that appear, on the surface, thoroughly inhospitable. That resilience carries real implications for the broader search for life beyond our own planet. If microbes can genuinely survive beneath several kilometers of ice here on Earth, they might well survive beneath the icy crusts of Europa or Enceladus. They might even persist somewhere in the deep subsurface of Mars, where liquid water could conceivably still exist far beneath the planet's frozen, radiation-scoured surface. Such discoveries would also meaningfully change how we think about Earth itself. Subglacial ecosystems, hidden and comparatively sparse as they may be, remain a genuine part of our planet's overall biosphere. They contribute quietly to broader biogeochemical cycles, transforming minerals, recycling nutrients, and potentially influencing the chemistry of meltwater that eventually reaches the open ocean. They function almost like time capsules, preserving ancient lineages and unusual metabolic strategies dating back to Earth's distant past. They serve as natural laboratories, showing researchers exactly how life responds to prolonged isolation, scarcity, and extreme pressure. And they stand as a quiet reminder that life isn't confined only to the comfortable, easily accessible places we're used to. It exists wherever it possibly can, sometimes in places we'd least expect to find it at all. A fragile kind of survival. But life beneath the ice, if it truly exists, would also be remarkably vulnerable. Its isolation is simultaneously its most defining characteristic and its greatest form of protection. A single careless drilling operation could introduce foreign microbes capable of outcompeting or fundamentally disrupting native species that have never once encountered anything like them. A small, seemingly minor shift in temperature or local chemistry could upset a delicate balance that has quietly sustained itself for many thousands of years. Even the simple act of exposing these hidden environments to light and open air, however briefly, could carry consequences we don't yet fully understand. This is precisely why researchers approach subglacial exploration with such extraordinary caution. They understand that they aren't merely searching for life in some abstract academic sense. They're potentially intruding into ecosystems that have never once encountered anything from the outside world before. They have to tread carefully, constantly balancing genuine scientific curiosity against a real responsibility to protect whatever fragile life might already be there. There's also a genuine possibility that any life beneath the ice isn't actively thriving in any conventional sense, but rather existing in some form of extended dormancy. Under such extreme conditions, microbes might spend the overwhelming majority of their existence in a kind of suspended animation, metabolizing so slowly that a single generation might stretch across many centuries. They might survive on only the faintest trace amounts of available energy, dividing perhaps once within an entire human lifetime, or even less frequently than that. They might represent relics from an earlier, different era, quietly clinging to existence as the world slowly changed around them over unimaginable stretches of time. If that turns out to be the case, studying them wouldn't just reveal how life manages to survive. It would reveal something deeper about how life endures, how it waits out hostile conditions, and how it persists silently across truly vast stretches of geological time. A search that reaches far beyond microbes. In the end, the ongoing search for life beneath the Arctic's glaciers is about considerably more than microbes alone. It's fundamentally about our desire to understand what life actually is and where it might reasonably be capable of existing. It's about carefully testing the outer boundaries of biology itself and meaningfully expanding our working definition of what counts as habitable. It's about drawing a genuine connection between Earth's own hidden biospheres and the broader search for life elsewhere in the universe. And in a quieter sense, it's also about a kind of humility, a recognition that our own planet still holds genuine mysteries we haven't yet solved, that there remain places entirely untouched by human eyes, and that life, quite possibly, is already thriving there, entirely without our knowledge or awareness. If researchers do eventually find life beneath the Arctic's ice, it would fundamentally change how we understand our own planet. It would remind us that Earth's story is still far from fully told. It would suggest that life isn't some rare, unlikely accident, but rather a natural and perhaps inevitable outcome whenever the right basic conditions happen to converge: water, energy, and sufficient time. And if researchers ultimately find no life at all down there, that too would teach us something meaningful about the genuine limits of biology, the fragility of potential ecosystems, and the particular uniqueness of the sunlit surface world we ourselves happen to inhabit. Either way, the search itself continues to matter enormously. It pushes our technology, our scientific understanding, and our collective imagination toward genuinely new frontiers. It draws together glaciology, microbiology, chemistry, and planetary science into a single shared pursuit. And it slowly transforms the hidden depths of our own planet into something like a proving ground for missions that may one day reach far beyond it entirely. Let your breathing slow even further now. We're lifting our gaze outward for a moment, toward distant moons that may be hiding oceans of their own, and then, slowly, we'll bring the story back home. A reflection held up to the cosmos. Far beneath the Arctic's glaciers, in those lightless realms where pressure crushes rock and water moves unseen through total darkness, there is something more than simply the story of Earth unfolding. There is, in a very real sense, a reflection of something considerably larger. For all their remoteness, the hidden lakes, winding channels, and possible ecosystems buried beneath our polar ice sheets aren't entirely unique to our own planet. The conditions that shape them, the cold, the darkness, the pressure, the isolation, the chemical gradients capable of sustaining life without any sunlight at all, aren't confined only to Earth. They exist elsewhere too, scattered across our solar system and quite possibly well beyond it, on distant worlds where ice hides oceans of its own, where liquid water flows quietly beneath frozen crusts, and where life, if it exists there at all, would have to adapt to remarkably similar challenges. In studying these hidden realms here on our own planet, researchers aren't only probing Earth's private secrets. They're effectively rehearsing for exploration elsewhere entirely, learning how to reach, understand, and carefully protect environments that may one day hold answers to one of humanity's oldest and most persistent questions. Are we alone in the universe? Europa, a vast ocean beneath the ice. The most obvious of these distant cosmic mirrors is Europa, one of Jupiter's 4 large Galilean moons. Slightly smaller than our own moon, Europa is a world defined almost entirely by ice and rock, its surface etched with countless cracks and ridges that quietly betray the movement of ice over liquid water hidden below. Beneath that cracked surface, beneath ice estimated to run somewhere between 10 and 30 kilometers thick, lies a genuine global ocean, one containing considerably more water than every ocean on Earth combined. That distant ocean is kept liquid not by sunlight, which barely reaches that far out into the solar system, but by something called tidal heating, the result of Jupiter's immense gravitational pull constantly flexing and kneading Europa's interior as the moon orbits its host planet. The end result is a world hiding a vast, dark, heavily pressurized ocean sealed beneath a thick shell of ice, an environment strikingly, almost eerily, similar to the subglacial lakes and channels believed to exist beneath our own planet's glaciers. If life exists there in any form, it would likely resemble the kind of microbial ecosystems researchers suspect might already exist beneath our own ice sheets, quietly drawing energy from chemical reactions between water and rock, or perhaps from organic compounds delivered occasionally through cracks in the overlying ice. Enceladus, a world that shows us its ocean. Enceladus, a considerably smaller moon orbiting Saturn, offers researchers a second compelling mirror. Beneath its bright, icy surface lies another global ocean, kept liquid by essentially the same tidal forces that warm Europa from within. Unlike Europa, however, Enceladus actually gives us direct, visible evidence of that hidden ocean's existence. Through narrow fractures near its south pole, it periodically sprays plumes of water vapor, tiny ice particles, and organic molecules directly out into space, material that passing spacecraft, including NASA's Cassini probe, have actually flown through and sampled directly. Those plumes have been found to contain dissolved salts, simple organic compounds, and tiny grains of silica, all of which point toward ongoing chemical interactions between liquid water and rock somewhere on the moon's hidden seafloor. They hint strongly at hydrothermal activity, the very same kind of process that sustains entire ecosystems around Earth's own deep-sea vents, and which may similarly sustain hidden life beneath our own polar ice sheets. If microbial life does exist within Enceladus's ocean, it might well be chemically and structurally similar to whatever life could exist beneath the Arctic's glaciers. And if a probe is ever sent down into that distant ocean, it would face many of the exact same fundamental challenges as a mission exploring Earth's own subglacial lakes, penetrating thick ice, carefully avoiding contamination, and somehow surviving within a dark, heavily pressurized environment, hundreds of millions of kilometers from home. A pattern that repeats across the solar system. And these two moons are far from alone. Ganymede and Callisto, two of Jupiter's other large moons, are both believed to hide substantial subsurface oceans of their own. Titan, Saturn's largest moon, carries a thick outer shell of ice sitting atop a deep ocean made of water mixed with ammonia. Even Pluto, once assumed far too small and cold to host any liquid water at all, may harbor a hidden subsurface ocean as well. And somewhere beyond our own solar system entirely, distant exoplanets and their orbiting moons may host remarkably similar environments, though we don't yet possess the technology needed to observe them directly. All of these distant worlds share several key features with the hidden realms buried beneath Earth's own glaciers: thick outer ice, liquid water sealed beneath it, available chemical energy sources, and prolonged isolation from any direct sunlight. They represent, in a sense, variations on a single recurring theme, and that theme suggests something genuinely profound. The specific conditions that make life possible beneath ice might not be rare at all. They may, in fact, represent among the most common potentially habitable environments found anywhere in the universe. Redefining what habitable even means. This growing realization has meaningfully reshaped how scientists think about the broader search for life beyond Earth. For much of the 20th century, that search focused almost entirely on planets with surface conditions resembling our own warm, temperate worlds where liquid water could exist openly in lakes, rivers, and oceans beneath a breathable atmosphere and direct sunlight. Mars, once considerably wetter and warmer than it is today, was long considered the most promising target. Venus, before scientists fully understood its runaway greenhouse effect, was briefly considered another. Even distant exoplanets are still frequently judged based on whether they orbit within their star's so-called habitable zone, the specific region where liquid water could theoretically exist openly on a planet's surface. But the discovery of hidden subsurface oceans on icy moons, combined with the growing realization that life can clearly thrive without any sunlight at all, has meaningfully expanded that entire perspective. Habitability, it turns out, isn't necessarily limited to a planet's surface. It may actually be far more common beneath ice, shielded from harsh radiation and comfortably insulated against extreme surface temperatures. Within this broader, updated vision of habitability, Earth's own subglacial environments become genuinely invaluable natural laboratories. They allow researchers to study, firsthand, exactly how water interacts with rock in the total absence of sunlight, how chemical energy alone can sustain functioning ecosystems, how life adapts to extreme pressure and prolonged isolation, and how microbial communities continue evolving within sealed environments across very long stretches of time. They allow scientists to test and refine technologies and techniques that could eventually be used on entirely different worlds. Drills capable of penetrating thick ice without contamination, autonomous probes able to operate reliably within dark, pressurized water, and sensors capable of detecting subtle chemical signatures of life under genuinely hostile conditions. Every single mission sent to a subglacial lake here on Earth, every careful experiment conducted beneath one of our own glaciers, functions as something like a dress rehearsal, not only for exploring our own planet, but for eventually reaching Europa, Enceladus, and worlds that lie even further beyond them. A two-way conversation between worlds. This connection genuinely runs in both directions. Discoveries made on other worlds also continue reshaping how researchers think about Earth's own hidden environments. Cassini's detection of organic molecules within Enceladus's plumes, for instance, highlighted just how important water-rock interactions likely are as potential energy sources for life. Interactions that almost certainly occur beneath Earth's own glaciers as well. Computer models of Europa's internal ocean circulation are actively helping scientists better understand how water might move beneath ice sheets closer to home. And the broader search for biosignatures, chemical, isotopic, or structural traces that might indicate the presence of life on other worlds, continues pushing researchers to refine their detection methods here on Earth as well, teaching them to identify subtle signals buried within complex data, to properly distinguish biological processes from non-biological ones, and to interpret ambiguous evidence carefully, yet with genuine scientific creativity. The striking parallels between Earth's own subglacial environments and these distant extraterrestrial oceans also raise genuinely intriguing questions about the origins of life itself. Some researchers believe life on Earth may have first emerged not in shallow, sunlit seas at all, but around deep-sea hydrothermal vents, environments rich in usable chemical energy, well shielded from harmful radiation, and particularly conducive to forming complex organic molecules in the first place. If life can plausibly begin in places like that, then it might just as easily arise beneath thick ice as well, wherever similar underlying conditions happen to exist. That possibility genuinely blurs the line between what we'd normally consider an Earth-like environment and something more properly alien. It suggests that the real difference between the Arctic's hidden lakes and Europa's distant ocean may ultimately be one of degree, rather than fundamental kind. And it implies that by carefully studying the life that may exist beneath our own ice sheets, we might actually be catching a glimpse of how life could plausibly emerge elsewhere in the universe. And perhaps, in some small way, how it first emerged here on Earth as well. Practicing for a much harder mission. This cosmic connection also meaningfully reframes how we think about exploration itself. Sending a probe through kilometers of ice here on Earth is already remarkably difficult. Attempting the same feat on Europa or Enceladus, worlds located tens or hundreds of millions of kilometers away, is considerably harder still. Communication delays alone make any kind of real-time control completely impossible across such vast distances. Power sources have to be compact, extremely reliable, and capable of lasting for years without maintenance. Instruments must survive years of travel through the harsh environment of deep space before they can even begin operating flawlessly in a completely alien environment on arrival. and sterilization becomes even more critical than usual, since contaminating another world with stray Earth microbes could potentially destroy the very evidence of native life that researchers are hopping so carefully to find. And yet, the underlying basic principles remain essentially the same throughout. A cryobot slowly melting its way through the ice of Europa would face many of the exact same fundamental challenges as one currently being tested beneath a glacier in Greenland. An autonomous underwater vehicle, eventually sent to explore Enceladus's hidden ocean, would rely on essentially the same navigation and sensing technologies as one already operating beneath an Antarctic ice shelf today. Earth's own glaciers, in this sense, function as genuine proving grounds, places where researchers can practice, refine, and perfect techniques for the far more difficult missions still waiting somewhere further ahead. There's a certain poetic symmetry in all of this. The same conditions that frustrate researchers here on Earth, the total darkness, the crushing pressure, the constantly moving ice, the ever-present risk of contamination, are precisely the same conditions that may be quietly harboring life elsewhere in the solar system. The same technical problems we need to solve here in order to reach our own hidden subglacial lakes are essentially the same problems we'll eventually need to solve in order to explore these distant alien oceans. And the same fundamental questions researchers keep asking about the Arctic's hidden biosphere. How does it survive? What actually fuels it? How does it continue to evolve? Are very likely the same questions we'll eventually be asking about Europa, Enceladus, and whatever else lies waiting beyond them. In this particular way, Earth's most genuinely inaccessible environments become something like keys to understanding the broader universe. They demonstrate, quite concretely, not just what's possible here at home, but what might plausibly be possible everywhere else as well. This same perspective also meaningfully reframes our relationship with the Arctic itself. It isn't merely some remote, inhospitable region sitting quietly at the edge of the map. It functions instead as a genuine bridge between entirely different worlds, a place where planetary science, biology, geology, and engineering all naturally converge. It's a place where questions about potential life on distant moons quietly become questions about life right here on Earth. And where whatever answers we eventually find here feed directly back into our broader search for life elsewhere in the cosmos. The Arctic's hidden realms serve as a quiet reminder that exploration itself isn't necessarily a straight line pushing outward into distant space, but something closer to a loop, an ongoing dialogue between the near and the far, between what's already known and what still remains genuinely unknown. What researchers eventually learn beneath our own glaciers directly shapes how we search for life beyond them, and whatever we eventually discover beyond our own solar system will, in turn, shape how we continue looking beneath our own ice. It's entirely possible that when researchers finally manage to pierce Europa's ice, or successfully sample the plumes rising from Enceladus, they'll find no trace of life there at all. It's equally possible they'll find something genuinely astonishing, microbes quietly drifting through darkness, drawing energy from surrounding rock and minerals, much as their distant cousins may already be doing beneath our own Arctic ice right now. Either outcome would teach us something fundamentally important about the broader universe we live in. If life turns out to be absent, it would demonstrate that conditions beneath ice, while genuinely potentially habitable, aren't automatically inhabited everywhere they occur. If life is present, it would strongly suggest that biology isn't some rare, unlikely accident at all, but rather a fairly common outcome whenever the right basic conditions happen to align. Either way, all of the careful work being done beneath Earth's own glaciers right now will have quietly prepared us to properly understand whatever we eventually find. This is the last stretch of tonight's journey. Let everything go now. There's nothing left to remember, nothing left to hold on to, just this last, quiet thought to drift off with. A frontier we may never fully conquer. Even if, one day, we finally solve every engineering challenge, master every relevant law of physics, and build machines capable of slipping through the labyrinth beneath the Arctic's glaciers as easily as a fish gliding through open water, there will likely still be some part of that hidden world we simply cannot, and perhaps should not, ever fully reach. Because beneath the ice, past the crushing pressure and the absolute darkness, past the rivers we cannot see and the lakes we cannot touch, lies not only a physical frontier, but a deeply philosophical one as well. It's the quiet realization that some mysteries were never meant to be solved completely, that certain questions need to remain at least partly unanswered if they're going to retain any of their meaning at all. And this, perhaps, is the deepest truth hidden within this frozen, ancient world at the top of our planet. It isn't merely a place we cannot fully explore. In some genuinely profound sense, it may be a place we should never fully conquer. Curiosity is not the same as entitlement. We are, by nature, a species defined by wanting to know things. Curiosity has driven nearly every meaningful leap we've ever made, from the very first crude tools to the first telescopes pointed up at the night sky, from crossing unfamiliar oceans to eventually walking across the surface of the moon. It has built entire civilizations. It has reshaped continents. It has sent machines drifting past the edge of our solar system and helped uncover the delicate structure hidden inside our own DNA. And it's that very same curiosity pulling us steadily northward now, into the cold and the dark, quietly asking what exactly lies beneath all that ancient ice. We genuinely want to know what kinds of worlds exist beneath kilometers of frozen water. We want to know whether life is somehow down there, how it might have managed to survive, and what it could possibly teach us about ourselves and about the universe we all share. But curiosity, as powerful and defining as it clearly is, isn't quite the same thing as entitlement. Wanting to know something doesn't automatically mean we're meant to know absolutely everything. The line separating genuine exploration from simple intrusion is often thinner than we'd like to admit. And beneath the Arctic's glaciers, that particular line matters more than almost anywhere else on Earth. For whatever ecosystems might exist down there, isolation isn't just a defining feature, it's genuinely everything. They've evolved, or simply endured, entirely without interference from the surface world for many thousands, or perhaps millions of years. Their delicate internal chemistry, their fragile balance, their very continued existence, likely depends entirely on that prolonged isolation remaining intact. To breach it, even with the very best of intentions, risks destroying the exact thing that makes it so remarkable in the first place. A single bacterium, accidentally carried down on a drill bit, could easily outcompete native microbes that have never once encountered anything quite like it. A small, seemingly minor rise in temperature, caused simply by the heat of our own instruments, could shift the delicate chemical balance of an entire hidden ecosystem. A single stray drop of drilling fluid could contaminate a pristine environment beyond any hope of recovery. These aren't merely hypothetical concerns either. They're documented, real risks, present in essentially every serious attempt so far to explore subglacial lakes and hidden channels, and they force us to confront a genuinely uncomfortable question. Is knowledge always worth whatever cost comes attached to it? Opening a sealed room. There's also a deeper question here about authenticity itself. A sealed subglacial lake functions in many ways like a kind of time capsule, a detailed record of conditions that may stretch back hundreds of thousands of years. It holds not just ancient water and sediment, but genuine information about past climates, ongoing geological processes, and the long, slow evolution of life itself. The moment we finally open it, we inevitably change it. Even working with the greatest possible care, even successfully avoiding every trace of contamination, the simple act of breaching that isolation alters pressure, temperature, and chemistry in ways that can never quite be undone afterward. It's a little like opening a sealed tomb. Once that seal is broken, Whatever lies inside is never again quite what it was before. If we genuinely want to study these hidden environments exactly as they truly are, rather than as they inevitably become the moment we finally touch them, then we have to accept that some part of them may need to remain permanently beyond our reach. This particular tension between our natural desire to know and our genuine responsibility to protect what we're hopping to study isn't unique to the Arctic at all. It shows up wherever exploration pushes into any genuinely untouched realm. It was present when we first sent probes toward Mars, forcing scientists to develop careful planetary protection protocols, specifically to avoid contaminating a world that might, just possibly, already harbor life of its own. It's present in current plans to eventually drill into Europa's ice, where any accidental contamination could seriously compromise the entire search for native life. And it's present, quietly, right here beneath our own glaciers, where the very environments we're hopping so carefully to study may be permanently and irreversibly altered by the simple act of studying them at all. None of this is really a reason to stop exploring altogether, but it is, perhaps, a genuine reason to proceed with real humility, meaningful restraint, and a sincere willingness to leave at least some mysteries only partially uncovered. A species still learning humility. Humility has never come especially naturally to us as a species. We tend to think of the world primarily as something to be mapped, measured, and ultimately mastered. We celebrate the exact moment a flag is planted, a sample collected, a photograph brought triumphantly home. We often measure progress simply in terms of what we've successfully claimed for ourselves. But beneath the Arctic's glaciers, that sense of mastery is largely an illusion. The forces truly at work down there, pressure, gravity, time itself, are older and considerably stronger than anything we could ever hope to build. The labyrinth hidden beneath the ice continuously reshapes itself, entirely beyond our control. Whatever ecosystems might exist within it have evolved completely independently of us, entirely beyond our influence or awareness. The very best we can realistically do is approach as careful, temporary guests, aware, at every step, that we're entering a place that was never really ours to begin with. There's genuine value, too, in simply not knowing everything. Mystery has always been part of what drives us forward as a species, but it's also part of what keeps us properly grounded. It reminds us that the universe is considerably larger and stranger than we are. It keeps us appropriately humble, genuinely curious, and reasonably cautious. It teaches us that our understanding of anything will always remain somewhat partial, that there will always be horizons sitting just beyond our current reach. The hidden world beneath the Arctic's ice is one of those horizons. It's a quiet reminder that even on a planet we've already mapped and measured so extensively, there remain places still entirely untouched, stories still completely untold, questions still genuinely unanswered. That's not really a failure on our part. It's simply a feature of living on a dynamic, ever-changing world and of our own complicated, evolving relationship with it. Why some secrets deserve to stay secret. Perhaps, in some deeper sense, this mystery genuinely needs to remain intact, because it quietly tells us something fundamental about life itself. Life doesn't thrive only in the places we can easily see and carefully measure. It also persists, apparently quite comfortably, in places that remain permanently hidden from us. It isn't limited only to what's obvious or conveniently accessible. It endures in total darkness, under crushing pressure in complete silence, well beyond our current reach. That kind of persistence is part of what makes life itself so genuinely extraordinary, and part of what makes our own planet so remarkable in turn. If we were somehow able to pierce every remaining glacier, drain every hidden lake, and expose every last isolated ecosystem to the light, we would undoubtedly learn a great deal in the process. But we might also lose something genuinely precious along the way. The simple knowledge that there still exist corners of our own Earth where life, if it's truly there at all, continues on entirely on its own terms, answerable to no one. The Arctic itself almost seems to insist on this particular point. Every single time researchers get close to uncovering its deepest secrets, something changes. Channels quietly close up, lakes drain away unexpectedly, the ice shifts without warning, equipment gets lost, entire missions fail outright. It can almost feel as though the labyrinth moves not purely because of ordinary physics, but because the mystery itself is quietly resisting us, demanding, in its own way, patience, genuine caution, and a measure of real respect. That resistance is undeniably frustrating at times, but it's also strangely instructive. It reminds us that real exploration was never meant to be a form of conquest. It's closer to an ongoing relationship, a genuine dialogue between what we want to know and what the world is actually willing to reveal to us, on its own terms and its own timeline. And like any real relationship, it depends heavily on trust, patience, and clearly respected boundaries. Discovery without possession. None of this diminishes the genuine importance of exploration itself. If anything, it quietly enriches it. It suggests that our ultimate goal isn't necessarily to strip away every single layer of mystery we come across, but rather to understand the world a little more deeply while still consciously leaving certain parts of it intact. It suggests that real discovery isn't always about outright possession, but sometimes instead about simple reverence. It suggests that the unknown isn't merely an empty void waiting to be filled in. It's a genuine presence, one worth quietly acknowledging on its own terms. Beneath the Arctic's glaciers, that presence feels remarkably tangible. It's there in the darkness that swallows every trace of light completely. It's there in the pressure capable of bending solid steel. It's there in the water moving quietly, unseen, and in whatever life may or may not exist within it. It's there in the simple knowledge that no matter how far we eventually manage to go, there will always be something waiting just beyond our current reach. And perhaps that's really the whole point. The hidden world beneath the Arctic's ice was never meant to be a single puzzle, solved once and then set aside forever. It's closer to an ongoing conversation, one that will likely continue unfolding across decades, across centuries, and quite possibly well beyond that. Each new generation will push forward just a little further, learn just a bit more, and inevitably leave a little more mystery intact for whoever comes next. We'll keep building better machines. We'll keep refining our models. We'll keep deepening our collective understanding one small step at a time. We'll make plenty of mistakes along the way, lose valuable instruments, and slowly learn from every failure. And through all of it, that hidden labyrinth will simply keep on moving quietly at its own pace. The water will keep flowing, and the darkness, patient as ever, will keep holding on to its secrets for however long it chooses to. A beacon, not a barrier. In the end, perhaps the greatest gift this hidden Arctic world has to offer us isn't really its answers at all. It's the questions it continues to raise. It asks us, quietly, who we really are when we're finally faced with the truly unknown. It asks how much we're genuinely willing to risk in the name of knowledge, and just as importantly, how much we're willing to consciously leave untouched. It asks whether we're capable of being explorers without also becoming conquerors, whether we can learn without inevitably destroying, whether we can find a way to honor what we don't yet fully understand. These aren't easy questions to sit with, but they're exactly the kind of questions that matter not only beneath the ice, but really everywhere we choose to explore. And so, as we look northward one final time tonight, toward the glaciers, the darkness, and the mysteries quietly waiting beneath them, we're reminded that real exploration was never simply about traveling farther. It's about going deeper, in every meaningful sense of that word. It's about coming to terms with our own small place within a world that will always, in some sense, exceed our full grasp. It's about learning to accept that certain mysteries are simply meant to remain. The Arctic's hidden world is one of those enduring mysteries. It resists us, it humbles us, and somehow in its own quiet way it continues to inspire us all the same. It challenges our ingenuity and it tests our patience and resolve. It reveals small pieces of itself now and then, only to slip quietly away again, leaving us, each time, a little more curious, a little more willing to imagine, and a little more willing to simply dream. That dream of what might be sleeping down there in the dark, of what secrets the ancient ice may still be holding on to, is, in its own way, perhaps more powerful than any single discovery we could ever actually make. It's what keeps us reaching, keeps us gently questioning, keeps us quietly striving forward. It reminds us, softly, that there is always more left to learn, always something more worth seeking, always a little more waiting just beyond the horizon. And in that sense, the mystery sleeping beneath the Arctic's glaciers doesn't need to be solved at all in order to matter. Not as a barrier standing in our way, but as a quiet beacon, gently calling us onward. Not as any kind of failure of exploration, but perhaps, in the end, as its truest and most honest expression. Sleep well,